Yes.
And on the second part, I am wondering if the paths that you take are not representative, that if there is a bias, like there is an overflow sometime, but you will never find it by an execution. So your probabilistic results are with respect to the set of traces that you have considered, not with respect to the model or system.
That's an excellent question. So this is something I should have clarified. The set of traces, we assume that there is an underlying distribution over the set of trajectories of the system, and that we can sample from this distribution. So the set of traces that we get are sampling from the distribution. So as long as the set of traces is representative enough about the distribution, and there are some techniques in the statistics field to check if your sample distribution and your actual distribution are close enough. You could use such techniques to do that for when you know the underlying distribution to be something pleasant, but for arbitrary distributions, it's a little hard to know. The conformal prediction guarantees that we get are distribution free and model agnostic. So they don't depend on the predictor that you use, and they don't rely on having an underlying known distribution. So in spite of that, you still get these guarantees, which is why it's a little magical. But once you go through the proofs, it kind of falls out of it. You're right, that you might never sample the one trajectory that hits a bug, but that's why it's a probabilistic guarantee.
You have the same problem as in Monte Carlo method.
Of course, yes, yeah.
So I had a follow-up to that. One of the reasons many of us do formal methods is we claim that we can get to corner cases, the cases that people didn't think of when they designed the system, and often formal method tool will point out, like, you're getting this corner case, and I didn't think about that, and then go fix the program. What's the role of all of that in this world that you're talking about that we are in right now?
There's a different set of people working on a different set of techniques that have nothing to do with what I presented here. Everything I presented here is with the goal of getting some kind of guarantees, assuming your system is correct, or hoping that your system is correct, right? So I don't think that you should use probabilistic, like conformal prediction like approaches to find
Thank you for the introduction. Right. Yeah, so we will continue in a black box way, but not with verifying an existing controller, but here we want to, on the one hand, build a controller. So we want to synthesize it. And we'll also look at a setting where the sampling is really expensive. So we want to get this controller from a black box system with only doing a few hundred samples on the black box system instead of the 40,000 or what we just had in the keynote. So I'll first give you a short introduction on what is the actual problem we're trying to solve. Then I'll tell you about how we are going to tackle it and then how we evaluated it. So what is the setting for this? So we are actually considering a relative. Oh. Stumbling about it. So simpler setup without, so not a feedback controller, but like a feed-forward controller, or like we have a stateless function f, which represents our system, which has two types of inputs. On the one hand, we have some input, some observable thing about the environment. For example, in our larger case study, this would be the temperature. So we have some system that is very sensitive to temperature, and this should produce some correct output, for which we are here assuming that we can just quantify this with one real valued value, which we call R here, and we want a system that keeps this always positive. We can plug in a specification to actually get this, but in the more abstract sense, it's just we want to have this function always gives us positive output. And then we have this block C. So this is the controller that we actually want to build. And this takes our input, our environment observation, for example, the temperature, and it can produce some additional control input to our black box function, like some trimming parameter to adjust for potential differences in temperature. So the system might behave different for different temperatures. And it also has one screw that you can turn to adjust it and to make it behave correctly for each of the different temperatures it might run. Okay, so now know briefly what we want to do. So how are we going to do this? Then we're considering a black box synthesis. So we don't have implementation, or not a white box inspectable implementation of this function f, but instead we want to run simulations or executions on our function and then build a model that is targeted towards finding this control function. So it doesn't need to be an exact representation of everything that goes on in this function, but it should be good enough for us to build this control function and to verify that this is actually a correct control function according to some additional assumptions. So the high-level loop for this approach is depicted here. We're starting with some random samples and build a very small or very inaccurate initial model. And we try to find candidates on this model and then try to verify the candidates, which we can do even if we have an infinite state system with some assumption I'll get to in a moment. And either this very candidate is already correct, then we are done and we can hand this control function to the user. If this verification fails, or if we do not find any candidate because maybe the model looks like there is no possible control function for this model, then we also have an exploratory testing component that just runs some additional guided tests to figure out how should the model look at different parts of the system that are currently underexplored, so we can open up new parts for potentially finding candidates there. So what is the model that we're going to use? So we're going to use the line triangulations to build this, which are really nice because they can give us these linear interpolations. So here you see on the very left of the white box view of the system, which we don't actually have, but it's nice for illustrative purposes. So this is some simple examples. So we have the inputs on the x-axis and what our controller inputs on the y-axis. So the problem of now finding this continuous control function in this two-dimensional case means we want to have a path that goes from the very left to the very right and assigns one control input to every input of this function. Now, if we run a few samples and triangulate them, then we might end with a graph like in the middle. And additionally, if we know the function values, which are color-coded here, then we can also build from this triangulation this linear interpolation model, which tells us something, oh, here in this area, the function is probably negative, here it is positive, and the black lines are the boundaries in the model of what the model believes to be good states where we are allowed to pass through versus bad states which we have to avoid. And I also show here in red the original level curves from the white box view, so we have some indication how good the model is at the moment. But since this is all continuous, we can't verify anything with just finitely many samples if we don't add at least some additional assumptions to that. And for that, we're assuming that our function, like the function of both the inputs and the controllables, is Lipschitz continuous. And we are also assuming that we actually know the Lipschitz constant, or at least the upper bound of the Lipschitz constant. So what does this tell us? It gives a boundary of how fast the output of this function can change. And using this, we can, using this in the existing samples, we can, for every point in the state space, get an indication of what is the highest possible value the function could actually be there, and what is the lowest possible value the function could be. And also for every point, we get some ball around it where we know all the, so we have like this sample here, and we know that all the samples or potential samples in this ball are also positive samples. Or for this negative sample, we know that everything here will also be always negative. And so we don't really have to sample these values again, but because we already know, are these good or are these bad? So now that we have our very first model, or we just started with some random samples, and we have to get good candidates, we have to explore a little bit and add more data points to it. So we use 3 different heuristics to do this. The first one is really simple, where we just randomly sample on a grid to get just some completely unguided samples, so we're not getting stuck with some kind of heuristic. The second one is going to use the Lipschitz information, and the third one is actually a combination of what we already know from our interpolation model and the Lipschitz assumptions. Explain the second two here with some examples. These plots are now moving into a one-dimensional space, which is not actually what our functions look like, because they were at least 2-dimensional, but they are much nicer to actually show that. So we have now 2 samples, and here are also shown what are the highest and lowest points that are possible according to this known Lipschitz constant. So the one orange uncertainty estimation would just say, if a point has a very high gap between the highest and lowest possible values according to the Lipschitz assumption, then the model is probably not yet very precise there, and there is a good chance the value might be wrong. And the other green one, which already takes into account the information we have from our current model, tries not to estimate just how large is the gap, but in some heuristic way, how likely it is that a positive point will be classified as negative or that the negative point is classified as a positive point. And for that, we're using the, on one hand, the sign of the point we want to estimate. And then we look, if since this is a positive point, how negative could the function actually be at this point? And in this case, the lower bound is already a positive point. So for this point, we know that it is positive. But if you look at slightly shifted points, then we have here again a positive point, but we have a relatively large possible negative value. So if this is a point in our current model, then without any like formal guarantees, but heuristically we can say this point is more likely to be mispredicted than this point or this point where the potential negativeness of a positive point is smaller than before. And the heuristic would then just take the current interpolation model and use some optimization method to pick points that are very uncertain according to our heuristics. And on this blue picture, you would see a heat map which shows you how, for this given model, how uncertain certain regions are. And you see here the highest uncertainty is actually here at the border where we have these very thin triangles. So these are kind of bad and we should break them up. And also here, if you look at this part, which passes through from one negative region to another one, but passes through something that is actually positive. And we see also here, oh, this actually has also a higher uncertainty than the surrounding points. So this predictor actually is somewhat good enough or for guiding it to say, oh, maybe we should sample more here because there might be a path hidden that we cannot actually find at the moment. So now that we have our first or a model after a few iterations, we should find our candidates. And for that, we're restricting our search here to edges of our triangulation. So we'll first remove all the edges that pass through negative points because they cannot be part of a function that is everywhere positive. And then, since we're looking for a function, we will also turn it into a directed graph. So we don't want to loop back and assign multiple control values to the same input. And then we use a simple graph search to find the shortest path or the path with the largest minimum value through this reduced graph. And we have the paper also describes a way how to make this complete by adding additional points. But in practice, actually, just searching along the edges turns out to be good enough and easier to handle. Now that we have this candidate, we want to check, is it actually correct? And for this, we can also turn back to our sampling or exploration heuristics and just pick the most uncertain points on our current candidate. So the candidate is always positive, so if we use this heuristic on how negative might it be, then we would sample first those points that might be very negative. And this leads to relatively fast classification of candidates that are spurious. And then we can use these additional points to improve our model, and ultimately we end up with an improved model and the candidate that passes through the model and is also positive everywhere. And what you see here is like the last model before doing all the final verification samples. So there are a few more samples along those edges that are then good enough that with these Lipschitz assumptions, we have a complete guarantee that this is actually a correct control function for this problem. So what kind of formal guarantees do we get from this approach? So the first one is that we're sound. So if we find a solution and our model has a Lipschitz bound that is not larger than whatever we assumed, then we will find a solution that is correct. We also have a guarantee that we are going to find a solution if one exists, with a small caveat that says that there should be a solution that is at least greater than some limit E or epsilon. So if the only solution that exists is one that passes exactly through 0, then we cannot find this with just doing finitely many samples. So you have to pick at least a tiny epsilon. And if a solution exists that stays that far away from the true-false boundary, then we will find a solution. And also, if there is no solution at all, then after doing a lot of samples, which is actually what we wanted to avoid, but I think it's still nice to have this guarantee that if you would be able to run a lot of samples, then we can also confirm that none exists. And for the case in between, we might get either answer. Okay, then let's see how well all this works. So we tried this on both some randomly generated instances and some cyber-physical system examples. Among them is one industrial case study for some voltage and current regulation. And we're going to compare our methods with two different baselines. One is a depth-first search that just uses the Lipschitz information to move as far forward as possible. And the other one is a template-based optimization method, which tries to find parameters for a piecewise linear function. So let's first look at the random examples. For this, we use this Perlin noise generator, which is from the computer graphics domain originally, which can give us nice random problem instances. And I plotted and showed you 4 of those here. So again, we want to find this path from left to right by doing just a few samples on this function. And as you can see, our method almost never needs more than 100 samples to construct the model and find the correct function. But both the depth-first search as the optimization method are not able to find solutions for about half the instances with a limit of 2,500 samples. If we make this whole thing higher dimensional, then the depth-first search method gets a bit better, but our triangulation method is still by far the best performing method on these instances. Yeah, we have some more artificial CPS problems and this voltage regulator. So this is our industrial case study. So you have this gray box here, which is what our algorithm assumes as the black box, but I also show you a few components, what is actually in there. So we have this analog band gap and the trimmer components. These are given as transistor level simulations in a SPICE simulator. So running a single simulation on that thing takes minutes for this example. So you don't want to run 40,000 simulations that each take 2 minutes. And what is the goal of this thing? It should provide very stable current and voltage outputs for all kinds of different conditions. And this whole setup is very temperature sensitive, both the analog part and this trimming component, which is then used to adjust the current voltage outputs from the analog band gap. And the specification component, which is also part of the black box, but for which we actually know the implementation. This is just comparing the current and voltage to the reference and giving us robustness, the worst deviation of either current or voltage. So how well are we doing on these examples? For the upper ones, which I briefly skipped, so let's just look at this band gap ones. Depending on which model we use, so we had 5 different models with different transistor speeds or configurations of this thing, and it took us, in the worst case, about 300 samples to build our model. In most cases, were about 150 samples that we needed, and both of the other 2 methods failed to find any solution within 1,000 samples. Okay, so to conclude this presentation, I showed you a black box synthesis method that can be used to build controllers or feed-forward controllers for black box systems by using a very small number of samples, but still giving a verifiably correct solution for this problem. Thank you.
Thanks for questions.
So I guess.
Yeah, it should.
Hello.
He can hear you.
So I guess you see this question coming. How do you learn the Lipschitz constant, right? And so I mean, I think that there may be ways of systematically learning the Lipschitz constant if you have some access to individual modules. But you could also learn the Lipschitz constant in the data-driven way as well, right? So what are your thoughts?
Yes. Because I actually had a slide in there, but I skipped it because of time. So we have a way, or we proposed a way how to dynamically find those Lipschitz constants. So there are methods to take data samples, and you can get an estimate of what the Lipschitz constant is probably going to be. The best ones are statistical methods, which are a bit problematic in our setup because we cannot guarantee any IID distribution or anything about our samples. Because actually quite the opposite, our samples are very focused on the parts where we already found candidates. So they are we have a lot of samples where we explored for candidates, and in the local search space around samples, around potential candidates, but we don't have like uniformly distributed samples or anything. So we use a simpler estimator, which is called the Strongian estimator, which just looks at what is the maximum difference between any 2 existing samples and then adds a safety margin to that. And you can use this while computing the model and then just update all the Lipschitz parts with the updated Lipschitz constant. And maybe also another thing, all this guiding of the sampling still works if you have a wrong Lipschitz constant. It's just that the final verdict is wrong. So having a different Lipschitz constant doesn't really shift what is the best point according to any of the heuristics. But the stopping criteria of I have found a solution that is correct might be wrong.
Any other questions in the audience? Maybe I have a question, more of a clarification. So your path is good to visualize for one input. What would you do if there are multiple inputs? It's no longer a path, right? It's more of a surface that's going from one end to another.
Yes. So the current method is actually focused on this with one input, but we might have many different outputs. So in this case, it really is a path. But as some future work, we already tried methods where we're actually trying to find these surfaces of multiple of multiple inputs as well. Where, as you said, then it's more like a cut through this space in the surface. But this is future work and wasn't part of this paper.
So the other thing, I looking at your problem, you could pose it as finding a path where you give the guarantee for the largest possible Lipschitz constant. So in other words, you could find a path that still works even if I increase the Lipschitz constant assumption, right? So you can get the most robust path in this problem. Have you thought about that?
Yes, this is actually what we are just to some extent doing, because here we're searching for the candidate that has this largest minimum value, which roughly corresponds also to the path which is the most robust to changing Lipschitz constants.
Very good. Very good. All right, so any further questions?
I mean, I have more of a clarification. So I don't think this is working, but okay. So my question was like, so is there any state in this function f, or is it time dependent?
No. So we're assuming a stateless function.
So I guess the follow-up would be,
but
if there is state, then it would, I guess, complicate.
Then yes.
Thank you so much. So we have the break right now. We'll be back at 11. So let's thank the speaker one more time. So I've been working with my students on I'll send you a paper that we
So he's going to get set up.
But I have to take it with me.
Okay, so this is a talk on automatic inference of relational object invariants, and it's presented by Harry.
Well, this is, I think, the toughest presentation for me because I have to stand here. This thing is right in my eye, so I don't see any of you. And apparently I can't move, but let's see. So this is joint work with Yusen, Jorge, me, and Isabel. Unfortunately, I am presenting. Yusen did the work he should present, but this probably by now we're noticing there's so many problems with visas in the US. We had a conference in Canada last year. Lots of people can come. It's just getting worse and worse. But you got me instead of him because of visas. So what I'm going to talk about is automatic inference of relational object invariants. So let me set this in. It's a very simple problem. We're kind of surprised there wasn't a solution like this before. We're just putting it out there. So the goal that we want to do is we want to do abstract interpretation, static analysis by abstract interpretation. We want to automatically infer properties of memory objects. So think like a buffer that has length and capacity, and you want to know length is always bounded by capacity. Capacity is always greater than allocated space. This kind of relationships. We want to analyze C code, but really not C code, but rather how it's compiled into LLVM. So we don't want to depend on some syntactic similarities of C. Sometimes in C, you have something that's sort of very clear and simple one line, ends up being a lot of generated LLVM code. So we want to be at this low level. And the challenge is that if you try to do this, if you just apply normal analysis that you have, you're going to discover that the way things usually are defined, anything that's in memory gets weak updates. And so you lose any of the relational properties. So I'm going to do a little bit of setup to explain this to you, why this happens. And then hopefully our approach will be very clear. So we're going to play with this program. This is a made-up program, but it's a sort of a good illustration that fits on one slide. What happens in the program, there's two parts. There's a loop and something that happens after the loop. Inside the loop, we allocate a whole bunch of resizable buffers. A resizable buffer in C will be two objects. One is a whole data. This is allocated at the bottom. We're not going to do much with it. It just has data. And the other one is a header. And the header is a descriptor of a buffer. Will tell you where the data is. It has a field called buff that points to data. It's going to have a field that tells you how much space the buffer has. That's capacity. And it's going to have a field that tells you how much of it is already used right now. That's the length. Right? You've all used vectors. You've maybe implemented things like that in like second year computer science. You should all understand how this works. You allocate a bunch of memory. Capacity tells you how much. Every time you add something, you increase length. Eventually, you reallocate. Here, we have buffers of different size. They're being allocated, stored in some array, they're actually of different size, but always length is less than capacity. Then later, we allocate a new buffer, and we modify something and stick it back into the same array. And what we really want to know is we want to prove that length is always less than capacity. Therefore, all the memory operations here and elsewhere are safe. Now, the first problem that we face here, in this case, is that we're going to have a lot of abstract objects because lots of things are allocated. That's a challenge. Our abstract domain will start exploding. We want to compress it somehow. And the typical solution that I think almost everybody does is something called allocation site abstraction. You basically say all objects that are allocated in one program location and one allocation site, they become one abstract object.
and they all share their properties, and they're represented as a summary object. You can play with this a bit. There's lots of directions where you can say whether it's really an allocation side abstraction, or you refine it further, where you say actually depends on some other extra context, or you merge multiple allocation side together because ALS. But at the end of the day, you break the program into finitely many abstract sites, and each abstract site gets an abstract object. You apply this to this problem, and then you're going to have one summary object that tells you about all this buffer that you allocated. Now, when you do this, and you try to run your analysis with this program, what you're going to discover is that, interestingly, the final invariant you want is representable, length less than capacity for all of the summary objects. But this invariant is broken temporarily when the program runs, especially if you look at the low-level operations, and restored only when the object is completely filled. So if you try to run it here, you'll see that actually after an analysis, no matter how precise your abstract domain is, you're not going to get length less than capacity, because somewhere in the middle, you're going to be updating length of a new object, but not yet the capacity of the new object. And now it's in a summary object. You have some objects which are in a bad state, some object in a good state. You get top as the abstract value, or maybe some bounds, and that's it. That is a problem we want to solve. Now, if you worked in this space, and if you've seen this before, then you immediately will tell me, yeah, but this problem is solved. There is a thing called recency abstraction. It's exactly your example. Okay? And if we go back at the example, this is actually what's done in abstract interpretation, also what's done in like almost every modern compiler. You do a little trick. If you look inside the loop, it's very clear that what is being accessed is just the last malloc. So you can single out this last malloc from the summary. And you say, until the address from the last malloc escaped somehow, I know that I'm updating this one specific object, the last malloc object. And then only when I'm done with this, I'm going to stick it back into memory. This is an abstract interpretation known as recency abstraction, where you separate your abstract objects in addition to which allocation site, whether it's the least allocated object or whether it is another object. Okay. So that solves this problem, the first loop. But of course, it creates another problem, or doesn't solve the problem. That's why we have stuff after the loop. Recency abstraction only works for the first allocated object. But often our code is not just creates objects when they're allocated. The code will often pull a buffer out of memory. The buffer has its invariants. It will modify stuff in the buffer. The buffer loses its invariant and eventually regains it. And then this buffer is stuck back into memory. And recency abstraction will not help with this. So this, okay, so this is an example of the recency abstraction. And so then this immediately sort of gives out our solution. So we want to update the recency abstraction to, instead of keep track of most recently allocated object, the most recently used object. So we're going to have the most recent, it's called the recency use abstraction. And so the rest of the talk is just to tell you, so you start with this idea, it seems very obvious. What are the challenges that you need to solve in order to get to the final solution? And how do we put all of this together? And of course, there's going to be experimental results, because that's the only way we know that it works. And so obviously, you'll see it works great. Now, I'm going to confuse you a bit. Maybe not. But in order to prevent confusion, I'm going to first talk about methodology so that you don't get confused. How do you define a new abstract domain, a new abstract interpretation? Well, one way is you can define a very fancy abstract domain, show how all of the operations are done and that they're sound, and you don't. But this sometimes is very hard if your concrete semantics is missing some important concept that you would want to have in your abstract semantics. If you still just go and design an abstract domain just as is, you're going to run into a big problem that your abstract domain will be very complicated. But really, just because you're trying to capture something in the declarative way of the domain from the semantics. So we're going to go a different way. The way we're going to go is we're going to give you a completely different concrete semantics. This is where the confusion may happen. I'm going to talk about the concrete semantics, and you may have two questions. One, well, how do I know this answer abstractly? And you won't until I get to the abstract domain. That's concrete semantics. And the second one is how are you going to convince anybody to build this architecture? It's stupid. I'm not going to convince anybody to build this architecture. This is just how I'm thinking. Okay? Another way to do it, if you want to do it more principled, you build the series of abstractions. You sort of start with your concrete semantics, you build an abstraction into the semantics you want, and then you build the abstraction for the analysis. But we're doing it sort of in a more concrete, hands-on way. We're just building a new architecture. Now, what do we want from this new architecture? We want to be able to say, to connect the concept, most recently used memory object, which is a very abstract concept if you want to think about it in terms of sort of a C memory model, what an object really is, to something very concrete, so that I don't have to just dance around you telling you, this is what most recently is and this is what isn't. I just want to have a thing in my memory model that I can point to. And so the way we were thinking about it is that it would be easy for us to do this if we think of a memory model with a cache. So imagine that instead of a normal memory model where you just grab a thing that you want, I give you a cache. Now, you have to compile your program to use this cache effectively. That's going to be left out from here. That's, if you compile it ineffectively, it's still sound, you just don't get the benefit. So what do you need to do? Whenever you have to access main memory, you're no longer allowed to do it. You have to bring memory into the cache. How much memory do you bring? Well, you have to bring an object into the cache. So if you want to access, say, address 500, you can't access address 500. You have to bring an object to which address 500 belongs. How do you know which object that belongs? It's up to you. Compile efficiently. You want to compile very inefficiently, you say, my cache is just my whole memory. All objects belong to just this one memory object. I just bring everything in. And then you basically get one summary. What we actually do once we get to an implementation is we have an analysis based on LS analysis that breaks memory into LS sets, and each LS set gets its own memory cache. So it depends on how fancy your compiler is. We're just talking about once you do it, what the meaning is. So what do we have here? We have a memory is divided into memory banks, so that whenever you allocate memory, you pick which bank. Ideally, you would want to have each allocation site has its own memory bank. Each memory bank has a cache. Every time you want to access memory, you go and load it into the cache. The cache, in addition, has a whole bunch of flags that tell you, what state is it in, is it used, not used, and so on. This is our concrete domain. It's a product of domains. We have scalars for registers and things like that. Memory, which is a product because of memory banks. And then each memory has the storage, which is just a blob of memory, a cache, which is basically one memory object, and a bunch of flags. And so in order to sort of give you a hint of how this works, I'm just going to quickly animate through an example of executing the program under this memory model. And again, remember, this is all concrete. So I know exactly which address I'm using. I'm not worrying about LSing and all of those things. It's just the memory model. So I'm in the beginning of a program. I set I to 0. Only the scalars changed. I come to allocate memory. I got a new address. In my storage, I now know this address is allocated. There's nothing in the cache. I come to assign plen I. Now, it looks like it's just one line, plen I. In low-level LLVM, it's actually a bunch of lines. I first have to get the address of P. Then I have to add the offset of len, in which case 0, which is a new address, a new variable now called plen. And then this variable, I'm going to have to store I into it. So I'm doing all of this. And then what happens is that I'm going to do this update. I know that the cache is currently empty, it has nothing in it. So I now allocate the object at address 1000 into the cache, and I write my value into the cache. So you see here, where is it? Here at the bottom, the 0 is written into the cache, not yet into the storage. And then it continues executing, things change. I is incremented at the bottom. None of this affects the cache. The object is still in the cache because we know that the last object we used was an address 1000. The cache remembers this. Nobody written to memory yet. It just stayed there. We allocate the second object. We now have the second object. We haven't used the cache. At some point, we start doing a memory operation. We now know that we need to bring 2000 from memory into the cache. which means we have to flush the cache first. To flush the cache, we go through the steps. So this is sort of the semantic step that we want, and this is the micro-architectural step that we want, right? We want a new object in a cache, new value updated, but in order to do this, we first flush the cache into memory. We then re-update the cache based on the new object, then we write the value in there. So, and once we get to the end, once we get to the last iteration, same thing. We have something in the cache. We're about to access a new object. We load the new object in the cache and we access it. I mean, hopefully by now it's all clear. The only question is like, why would somebody build this architecture? So we don't want to build this architecture. What this architecture gives us, it gives us all of the necessary mechanisms in order to layer our abstraction. So we can show, and it's quite sort of obvious, that this memory model is compatible with the C memory model. I can easily write a compiler that will compile towards this memory model, and if a program is sound for C memory model, it will have the same behavior on this one. I can have a fancy compiler where I have lots of different memory banks, and I try to optimize this. And I can have a less efficient compiler. That's up to me. So now if we want to build our abstraction, so we get to the abstract domain. All we have to do, all I have to explain to you, is to explain how we layer the different domains. Okay. So now we know what the most recently used one, that's a cache. I need to have enough knowledge to know when to flush the cache. And I need to somehow propagate information across all of those different pieces. So this is how my abstract domain looks like. Again, it's going to be a product, modeling sort of what we have concretely. There's going to be an abstract domain over cache. We really want to think about it as some kind of relational domain like octagons. Otherwise, this is less useful. There's some domain for summary, probably the same as for the cache. We're going to move from summary to cache and back. There's domain for flags. They're Boolean, so we can represent them more or less precisely. There's domain for scalars, which is registers. Again, we have some fancy domain for this, probably also octagons, maybe even fancier. And then the important part is we need to keep track of all of those memory addresses to know which one is loaded where. And we don't want to put a lot of effort into it because we don't have any specific allocator. So if I tell you that a memory address is in some range, well, that really doesn't mean anything because it all depends on how allocator does it. And so we're going to add a whole bunch of equality domains to keep track just of equalities. So what we really care about is whether the cache is being accessed by the same address or from the same base address as it was recently. If it wasn't, we flush. If our equality domain is imprecise, or the program is written in some strange way, where, for example, it gets one object from memory, updates one field, then gets another object in memory, updates another field, and keeps switching, as opposed to getting an object, ensuring that it satisfies its object invariant, and then moving to the next one. So in one case, we'll do badly, and if a program is written well, we'll do well. In both cases, we'll be sound. So the trick here is really picking out these domains and figuring out how to do all of the reductions. Because if you try to be very precise at every step, this is just too expensive for this model. So again, just like before, I'll run through an example. And I think I'm kind of low on time. So this is a very detailed example, really meant if you want to sit down with the slides, click on different things and see what changes. Hopefully understand where this is going, so I'll just run very quickly. Just kind of get to see which parts of which picture get to change. We start in the beginning. We don't have any equalities. We know that I is 0. We have nothing in the cache, no summary. We start to allocate an object. We have an address. Now we abstract. We don't know it's 1,000, but we know it's not 0. We assume that malloc doesn't fail. We then compute plen. We know that plen was obtained by pointer arithmetic from p. Therefore, their base addresses are the same. So that's the first equality we get. We then we know that len equals I, and we know that the object that we need to go into the cache is the same object as p base and plen, the one we're accessing. And then, of course, eventually the result gets in the cache. At a strong update, we only had one object, This is just like recency abstraction, but just slightly for different reasons. It's not because it's last allocated, it's because it's the last address that we knew that is being used in the cache. And then this continues. So as we go to the second object, again, before we started using memory, nothing changes in the cache, it just lives in the cache. Once we get to start using memory, we have to flush the cache. This is sort of modeling the same microarchitectural steps, but now abstractly. And you have to keep track of where the equalities flows. But mostly we just move the cache line into the summary line. And then we come back, and now we can use the second cache, and so on. At some point, we're going to come to a join. So this is a join of the loop. On one hand, we have one object allocated, and it's in a cache. On the other hand, we have two objects, one in a cache, one in main memory. We have to join. Of course, the different ways to do it, and the solution that we pick is we flush before every join. So we see that an object on the left is in the cache. We flush it into memory. Now we have, and the second object, we also have an object in the cache. We flush it also into memory. And then we join the two using the normal join. So what will happen here is that we do get to keep that length is less than capacity, but we do lose the fact that on one hand, length is 1, and on the other hand, the length is either 1 or 2, depending on which object you're in. So smoosh them together. And same will be with widening. When you have to do widening, the same thing. You flush into summary and just do normal widening. And OK, so this gives you the invariants. And then if we want to do a write after the loop, you can see what's going to happen. It's the same thing. We have this object invariant in the summary. We bring it in. We modify the loop, the element. We know that the object in the cache is the one we're accessing. We do strong updates. And then when we're done, we get to keep the property. Perfect. So let me stop here and see if there's any questions about what we do before I go into how amazing it is. OK, so I think there was a question behind you first. No, wait. There's a question there first.
A quick question. I'm in CPS. I'm completely not in the field, but I'm just curious, like, if you have different applications, will this be challenging? Because like your cache utility, right? You don't want to flush other applications' data into the
So remember how I said I will confuse you? I managed to succeed. Good for me.
no, because I'm not in the field. So
No, this is great. So the cache here is just a mechanism for me to be able to say, before the cache is flushed, I do some abstract step. So I introduce this notion of a cache so I can make this kind of statement. And then I say, well, whenever you compile your program into this architecture, of course, you should minimize the number of flushes. If you have a lot of flushes, it's going to be imprecise. You're going to lose precision. It's going to be inefficient. If you manage to compile a program with few flushes, it's going to be more precise. I'm leaving out how do you compile into that architecture. That's outside. All I'm claiming is that I can compile my programs into this architecture efficiently. Not telling you how, but trust me, and I give you my code. And I'm claiming that if you compile into this architecture in any way, my result is sound. Okay? So your point is when you look thinking about the cache is correct. Like, how do you do this efficient compilation? I'm leaving this out.
thank you so much.
Cool. So it sounds like the cache has exactly one object in it, right?
It can have more.
OK.
And
that's kind of my question.
The abstract domain for the addresses can be more refined. So we chose one. And I mean, I haven't shown you yet the empirical results. And you'll see it's not as rosy as you may think. And so having more objects will make it even harder. So that's sort of the thing. But conceptually, sure, you can have lots of them. And all you have to do is just manage your address domain has to be more advanced than just simple
knob
equalities.
you can control to have more precision, but more complex, right?
Well, for example, you may want to say I have two caches because I have objects actually from two different allocation sites, two different types. And I have one cache for buffers and one cache for something else. But then in my abstract domain, I need to be able to know if I have an address, what address is it? Because if it's always either one, then I'm not going to benefit from the refinement in caches. You have a clarification comment?
Yeah. must alias, is it in the alias domain, the equality, is it must alias or may alias or something else?
I don't understand may and must alias as terms. I don't know what they mean. The domain that we have is a domain of equality. And so either you know that the pointers that you're writing to equal the pointer, the object that the cache keeps.
Okay, so it's a must alias, in fact.
Okay.
Yeah.
But we don't compute it as an alias analysis. We just have an equality domain, right? And so part of the abstract domain, that computation happens.
Okay, maybe you should go to the results and then we'll come back to the question.
All right. So this has been implemented. This has been validated and repeated. It's amazing. Now, for experiments, since I'm running out of time, I'm going to try and summarize my problem with experiments rather than the experiments themselves. This kind of work is really hard to evaluate, at least for me. The difficulty is that we want to know if it works. So we can run scalability. Then we need large programs, but then we don't have properties for them. What do we know? We can say, let's do memory safety on a large program. You do memory safety on a large program, you're never going to succeed. You're never going to prove it completely safe. So now you can say, I prove 80% of the checks. But how do I know that those 80% are actually the hard ones? Maybe the 80% are easy and there's like one that's hard and whatever I do made no difference. On the other hand, I can do small programs, but then why do you need this kind of technique? Why won't you just lower everything to SMT and do it in that way? So we try to address this a bit by trying different ways to evaluate it. We have some evaluation that looks at scalability, which takes a previous technique that we also developed, takes a corpus of small programs, but large, they're like hundreds of thousand lines of code, and we show it scales how we expected because we cut the abstract domain into small pieces rather than one big octagon. It scales how we expect. We have experiments for precision where we craft special programs that we know would be really good for our technique, shouldn't be handled by, say, recency abstraction and other tools. We compare it with MOPSA, and yeah, we get exactly what we expect theoretically, that this technique works well and recency abstraction doesn't. And then we embed it into a bigger pipeline. This is sort of what gave us reason to work on this in the first place. We have a case study where we're using bounded model checking to verify real AWS code. The code is small, but we verify complete memory safety of it. And we thought it would be cool to put an abstract interpretation pipeline up front and in the middle. Up front, because this is BMC, so it cuts loops. So up front is before you remove the loops. But then after you cut the loops, there's still a lot of reasoning that you can do with abstract interpretation before you go to SMT solving. So we also put this technique after the loops have been cut. And we compare how much effect it has on BMC. And here the results are very mixed. Again, there's a lot of details and numbers and things that you can look better in a paper. But the big problem is that if you start to work with BMC, you start finding SMT solvers that are not monotone. So for example, we can show we do pretty good at removing checks that an SMT solver doesn't have to do. This doesn't necessarily make SMT solver faster. Sometimes it makes it slower. And so still work to do how to integrate this in such a way that it's always, always good. But it's definitely something that you want to have as part of a pipeline because it does give you benefits. So that's it.
Time for a question.
So one question I had is, can you actually try to extend this to prove properties that are very hard with this materialization, summarization, recency abstraction? So for example, if I had a buffer where things later in the buffer, like in your resizable buffer, things later in the buffer are larger than things earlier, you might have to reason about two objects at the same time, right? Could you try things like that with now that you can materialize multiple objects in your cache?
Right, like this is the direction. Actually, when we started, we thought this will be easy. And then we'll do fancy things like multiple objects in a cache or separate, but this was hard. So it's conceptually easy. Then getting this idea, we can just change the concrete semantics, so it's very easy for us to think about it concretely and then what the abstraction means, that's easy. But getting this to work, the part that I skipped is fine-tuning all of the reductions so that you're actually still effective. That was hard. But yeah, like this is, and I think thinking in terms of this architecture that we can just add more things like caches and various things, and then we abstract them separately, that's maybe a good way to think about this kind of problems.
That sounds very elegant, actually.
Last question, and could the next speaker please come?
Oh, thanks, Harry. I was wondering the invariants that you are able to infer. Can you also infer quantified invariants with quantifiers, like universal and existential quantifiers?
I mean, only by reducing that to the quantifier free reduction, right? Like that sometimes you can reduce, for example, you say I have an invariant over a free variable, only in that way. So like to answer you then, no.
Okay. Thanks again.
Yes, it's working. Yes.
Yeah, just I think stay away from the speaker because
Yeah, there is a feedback.
So the last talk is about quantum programming. So Nicola is giving the talk.
Hi to everyone. I'm Nicola Solini, and in this talk, I will speak about static analysis that is built for detective entanglement inside of quantum program. So we are speaking about quantum. So, it doesn't work. Okay, now it's working. All right. So, okay. So let's start from the beginning. In quantum computing, we are working with the smallest information unit is the qubit, different from the classical world. So from a mathematical point of view, a qubit can be represented with a vector in a two-dimensional Hilbert space. Thus, to represent a qubit, we need two bases, since we are in a two-dimensional Hilbert space, that usually are 0 and 1, that correspond to the classical value 0 and 1 of the bit. Then we will have two complex coefficients, since an Hilbert space is a complex vector space. And a value of the qubit will be a linear combination of these two base values. And here we see the main difference with the classical computation, since the value of a qubit is a linear combination, or as the figures say, a superposition between the two values. This means that a qubit is not only 0 or 1, but can be both 0 and 1 together, with some amplitude that are indicated with the complex coefficient. So we are talking about entanglement, so we need to consider a system in which we have more than one qubit. For example, let's consider a 2-qubit system. When we put together 2 qubits, first of all, we need to build this vector space of these 2 qubits. How we build it? We build it putting together the vector space of the single qubit using this operator that is a tensor product. So in this case, since we are combining two bidimensional Hilbert space, we will get a 4-dimensional Hilbert space. So we will have 4 bases that are basically the combination of the 2 bases. And the state of a 2-qubit system, it will be a superposition of these 4 bases. In case we have 3 qubits, we will have 8-dimensional, so 8 bases, and so on. Thus, we have seen that when we are putting together qubits, we can obtain the vector space of the qubit using the tensor product. So there is one question that arises, is since the vector space can be obtained in putting together the single vector space, is a state of 2 qubits the result of a combination of the single state of the qubit? The answer is sometimes. In particular, when we can write a 2-qubit state as a combination of the single qubit, this means that the 2 qubits are separable. So we have 2 independent states, and the state of the global system, it will be simply the combination of these 2 independent states. like in classical computing or probabilistic computing. Instead, when we cannot write a state of 2 qubits as a combination of two single state, it means that these 2 qubits are linked together, and their state cannot be described considering 1 qubit only, but we need to consider these 2 qubits together. And this happens when the 2 qubits are entangled. So when 2 qubits are entangled, basically, we have multiple qubits that correspond to a single state that cannot be broken. We can see an example. For example, if you have like this state that is a superposition of all the 4 bases, we can write it in this way. So in this case, Q0 and Q1 are separable. And you see that we have Q0 that is a uniform superposition between 0 and 1, and Q1 that is 0 plus 1. So in this case, they are independent. Instead, we can have a state like this one, in which we cannot separate the state of the single qubit, because you see that the first qubit is 0 only when the second is 0. Similar with 1, the second qubit is 1 only when the first one is 1. So it means that the state of one qubit depends also to the state of the other one. And like in this case, we have the Q0 and Q1 are entangled. This the entanglement property is a powerful property. It is used in a lot of algorithms, but can cause also some problem because, for example, if in this state we decide to measure the first qubit, so we do an operation only to the first qubit, here you see that the first qubit is 0 plus 1, so the measurement will give us 2 results. The measure it's a probabilistic operation, so we'll have a different result. In particular, we can have the first qubit is measured as 0 or measured as 1. But since the 2 qubits are entangled, if after the measure, the result of the measurement on Q0 is 0, we are basically here. It means that the second qubit will be 0. No more superposition of value. Similarly with 1, if we measure 1, we are here, and also the second will be 1. So you see that where we are working with entangled state, if we work on 1 qubit, we are also changing the state of all the other qubits that are entangled with that one. For this reason, inside of quantum programming language, it's important to understand which is the entanglement relation, because we may have some operation, some variable that are also altering other variables that we don't know. And this is the aim of this analysis, understanding which are the entangled, approximating the entangled relation between a variable inside the program. So before introducing the analysis, let's introduce the language that we have used to define the analysis. We are using this regular expression language that is useful because it has a really simple syntax. You see that we have the first command that corresponds, that also the other nice things of this language is that this language directly corresponds to a control flow graph. In particular, we have 3 constructs. We have the sequential composition, the branching, and the iteration. And then we have the label that correspond to the label that we put on the edge on the control flow graph that are the statement of the language. In particular, we consider 2 special statements that are measurement 1 and measurement 0 that are useful for building conditional statement. For example, with the if-then else, we can build the usual if-then else that there is in quantum programming languages. That is an if-then else in which we have a quantum guard, and according to the result of the measurement of Q, we choose C1 of C2. We see that in this case, we can write this statement using our syntax in this way. So we have a branching, and we say if the measurement of Q return 1, do C1. If the measurement of Q return 0, do C2. Then we have the 3 quantum statement. We consider only these 3 simple operations because in quantum computing, using only these 3 gates, we can model every possible quantum computation. So it's useful for defining the analysis. In particular, the operations that we are considering are the Hadamard gate. It is like the most quantum gate in quantum computing because it's the gate that creates superposition. So if you have 0, it creates 0 plus 1. If you have 1, it creates 0 minus 1. Then we have the T gate that is a rotation, and it applies a rotation of pi divided by 4 to the second part of the state. And then we have the control knot that is a control knot. So we negate the second qubit if the first one is 1. You see on this example, we have a 0, 0 1, 0. After the C naught, we will have 0, 0, because the first one is 0, so we do nothing. And then here, the first one is 1, so the second one became 1. And we'll see that the C naught is also the gate that introduces entanglement, like in this example. So the second ingredient of our analysis is the abstract domain that we use to represent entanglement. In particular, with this abstract domain, we want to achieve two goals. We want to represent the entanglement relation between qubits, and also we want to try to approximate the value of the qubit during a computation. So let's start from the first task. The most naive way to represent an entanglement is if we have a state like this one, in which we have two entangled, in which we have A and B that are entangled together, and C and D that are entangled together, and A and C and B and D that are not entangled, because we can separate the state in two. The most naive way to represent this entanglement relation is considering the set of the variables, so A, B, C, D, and using a partition of this set. So we can use two sets. This set say that A and B are entangled together. This set says C and D are entangled. Since C and B, for example, are not in the same set, it means that we can separate the state here. However, using only this representation is not enough, because as we see in this example, if we consider the two parts of this state, and we decide to apply a control knot operation to both this part, you see that in the first case, if you apply a control knot operation between A and B, so we act on this part of the state, after the control knot operation, we will obtain this state that is still an entangled state. Instead, if we look to the second part of the state, and we decide to apply a control knot operation between C and D, you see that after the control knot, we obtain this state in which D is no more entangled with C. So this means that the relation between C and D and the relation between A and B are different, because they are both entanglement, but like the level of entanglement is different. And in particular, we are interested in tracking this kind of relation, because when two variables are related like C and D, with a simple C naught, we can separate them.
When you say abstract domain, in fact, this is in the concrete.
Yeah, I mean, yes, this is in the concrete, yes. This would be the abstract, and then we are building the abstract. Yes, I mean, this happened in the concrete, yes. And we want to represent what happened with this particular feature in the concrete in the abstract domain. So what we want to represent is basically when there are this relationship, this kind of relationship, that we call C-naught separable in this presentation. So here, graphically in this presentation, we represent this relation using a line. So in our abstract domain, it will become a partition of the set of the variable plus this additional operation that say these two variables are C-naught separable. So in our analysis, we know that when there are this relation, with a C-naught we can break the entanglement. Then the other,
Question.
yes?
Do you just do this for C-naught? Because I could hit it with a Hadamard, then
Yes,
then I
yes.
hit it with
No,
Hadamard,
in this work we do only did with the C-naught. Okay. We plan to try to improve the representation, consider more complex level. And there is an example after that show also the loss of precision. But yeah, we consider only the C-naught for now. And okay, the other goal of our presentation, of our domain is to represent try to approximate the value of the qubit. So let's see a couple of examples that show which are actually the value that we need to represent. Let's start for this one. You see that if we have a state in which the first qubit, the controller in this case, is a classical value, since the controller is classical, the control knot will be the same as a classical control knot operation, and thus we don't introduce entanglement. Then there is another case in which we have the controller that is a quantum state, but the target is this particular state, that is the state in which we have a uniform superposition between 0 and 1. And when the target is in this particular state, you see that the C-naught basically is equal to the identity. So also in this case, we don't introduce entanglement in the C-naught. And then we have this final example in which we have the target, the controller that is a quantum value, and the target that is a classical value. In this case, the C-naught introduced the entanglement and also created that particular relation to have seen before. So in our domain, we are interested to tracking where the qubits are in classical value and also in uniform superposition. How we try to do this? We introduce some label. First of all, we introduce a label that corresponds to all possible classical value and a label that corresponds to all value in which we have a uniform superposition between two bases. So this counted also 0 plus 1, for example, but also 0, 0 plus 1, 1, and so on. So we will have a lattice like this one, the two labels top and bottom. However, in our language, we have the T-gate. And if we try to represent the semantic of the T-gate on this lattice, we obtain this. We have with the classical label that is OK. But if we apply the T-gate to the set of value in this label, we go directly to the top. And of course, this is not nice. So to improve the precision of the T, we can add other three labels, because the T has this interesting behavior in which if we apply T 4 times to a value in the X label, we come back again to the X label. Quindi simply adding other three labels, we are able to represent the T in a more precise way. Then we also add this other label S, because it's very interesting when we do a join between one of these 4 labels, we obtain a state in which we always have a superposition between two bases. You see that the only difference between these 4, is the phase, but we always have B plus minus B, the negation of B. So we introduce also S, that is every state in which we have a uniform position between two bases, and then we have the top and the bottom of the lattice. So how we put together the label with the domain in the abstract domain? As we have seen before, when two qubits are entangled, there is no meaning in describing the state of the qubits separately, but their state corresponds to a unique state. So we decide to associate a label to each set of entangled qubits. In particular, in our example, we have, let's recall the label, we have this state that unfortunately does not correspond to none of this label because we have a superposition of 4 bases. So we label this at top. Instead, in the second case, we have a uniform superposition between 2 bases that correspond to the X label. So we can label it at X. And this is the representation of the state in the abstract domain. Let's see how we use it on a simple program. We consider this program, which there is no control flow graph, as simply a sequence of operation. So we start from, we can assume that at the beginning of the program, all the qubits are in the 0 state. This is a normal assumption in quantum computing. So in our abstract domain, we will start from a state like this one, in which we have all the 3 qubits that are separable and classical. Then we do the Hadamard gate to the first one. So we change the label to the first one, to classical, to uniform superposition. Then we do the first CNOT, that is a CNOT between a quantum value and a value that is classical. So the relation is to become a CNOT separable relation, and the semantic of the abstract semantic of the CNOT give to the pair the label of the target, of the controller. So since the controller is X, when we do the control node between a quantum value and a classical value, we obtain this relation with the label of the controller. The same happens with the third CNOT, since the controller is a label X, in particular is A. The target is classical, so we will have this relation. You see that it corresponds to this, in which we have a uniform superposition between 2 bases. Then we do a CNOT between 2 values that are CNOT separable. So of course, we delete the entanglement. So what happens? The target, it becomes a classical value, and it is no more entangled with the rest of the qubit. How it happens here. Here, now we decide to apply an Hadamard to A. And here we see where we lost precision. In fact, since we apply an Hadamard to A, we pass to this state to this other state. So we are not more in a state in which the qubits are CNOT separable, and it's no more a state that are related to some label. So unfortunately, we have to remove this line and to change the label as top. So basically, what we have here with ASC, that the value of ASC is basically the top of the lattice, because we consider them entangled. Since we want to approximate, given an over-approximation of the entanglement, here they are entangled, so there is no more information. basically this corresponds to no information about A and C, and the label is stop. In fact, if at this point in the program we decide to do these two operations that nullify the entanglement, okay, if you apply this operation to the abstract domain, since basically this part of the test does not contain no more information because we say simply entangled, we don't know the state, they remain entangled. So here we see that is connected to your question before. We see that where there is the loss of precision because for now we are able only to represent this kind of relation. And okay, so in conclusion, we have introduced this static analysis. The goal of this static analysis was to improve the state of the art. In fact, in the state of the art, there was only this kind of representation, considering the qubit together without trying to represent the entanglement relation between entangled qubit. So what we have done is to introduce this C0 separable relationship that allows us, in some situation like this one, to separate the qubit. However, we have seen that this is not enough, since the entanglements are a really complex phenomenon. In fact, as future work, we aim to try to improve the representation, so getting more in a direction in which we have a more complex representation of the entanglement, and also try to test and implement this analysis considering a more complex language with more gates, and also to give like a use case and some testing with real languages. And thank you for the attention.
Questions? We have lots of time.
So I wonder why you just focused on C0. So for example, you could have handled the Hadamard by saying, if I apply Hadamard twice, that's identity, right? So you could have expanded your domain. Why did you choose to stop here?
We choose to stop here because these ones, like for example with the Hadamard, because this relationship can be defined using, I have like an example here. This relationship can be defined using the measurement. In fact, here, when we have like the C0 separable property, you can define the states that are in this property, checking what happens when you do a measurement. In fact, when you have like the C0 separable property, it happens that if you measure one qubit, the other that are C0 separable with them collapse directly to a classical state. That don't happen in a general quantum state, in general entangled state. So like this property was like the property that was that we managed to define it in a sound way. For this reason, we only consider C0, because with other gate, like with Hadamard, for example, you can say this is a C0 Hadamard separable, but it's like listing the gate and then try to coming back. So this was the reason.
Do you know the exact complexity of this problem? I mean, if you didn't want to solve it without...
I mean, classifying entanglement state is NP-hard, with a lot of them. And yeah.
Can you extend your approach to support, for example, Toffoli gate control NOT?
Yes. Okay, yeah, like in this work we consider, like also for giving a more clear definition, we consider only that tree operation. But in general, like you can extend the approach. We only have to define the abstract semantics, considering a different gate. So yeah. With Toffoli gate, it probably will be more difficult to. There's some feedback. Right. It will be some problem probably to catching when you create a C0 separable gate, because you can have like it's depend. I mean, you have more cases because since you have two controllers, you can have one controller that is quantum, the other is classical, both are quantum. So probably you may find the more problem is trying to get the C0 separable property. So that is the main problem. So, yeah. But in general, you can.
More questions? Actually, I have one because this
Okay.
is all new to me. So I
All right.
want to go back all the way to your motivation.
Yes.
And I was trying to understand why analysis of entanglement is important.
Okay. The main reason is the first example because okay, let's go in the presentation.
I mean, I know what entanglement is.
Yes.
I'm just trying to understand why.
Yeah. Yes. This basically explains. Okay. Because basically, here we see that when we have entanglement, if we measure one qubit, and this also yes, and this also happens with other operation. For example, if you change the relative phase of the first one, you also change the other one. So, like in first of all, it's important because if you want to analyze, in general, you want to know like which operation. On which variable you are working on. It's not like in the classical case in which if I write measure Q0, I'm not only working on Q0. And this is related also to another problem which in quantum computing, if you want to like drop a variable, like remove a variable from the memory, this corresponds to a measurement. So you not always can do it safely, and knowing which are the variable entangled with a particular variable can give you an information to know, like if I measure this variable, what because basically a measurement broke something in the state, so you know also which are the variable effective of this operation, and in general with all the operations.
So in your program, it might look like you're only measuring Q0.
Yeah, exactly.
But actually, you're also
Yes.
collapsing the state.
Also of Q1, yes.
Yeah.
So yeah, this is the
It's
main.
like a hidden bug in your program.
Yes, exactly. Yes, that's the point. Yes.
That's the reason.
Yeah, it's similar. I mean, if you have the things that is closer to this in classical computing can be like with the alias or the pointer, which you changing one pointer, but you're actually changing maybe some other. Yes.
So no more questions? Then let's thank you. Before you go, there is Deborah wants to make an announcement about lunch. So if you
So can we switch? Hey.
Let there be light. Okay, that sounds better. Okay, so this is mostly a theory talk about the complexity theoretical result. So there will be no experiments, no implementations or so. And I guess that also some people here are not very familiar with the framework. So I'm mostly keeping this on a high level, trying to give you an idea of what's going on here. And so if you're more familiar with this, I'm sorry. So what's a recursion scheme? That's a higher order grammar that generates a tree. So it looks like this. So you have non-terminals, just like in context-free grammars or so on. But these non-terminals can also have arguments that are also typed. And then you can say, for example, that the non-terminal A, if you give it something, then derives something that depends on the argument. So in this case, this argument here would be a tree, and then the non-terminal does something with the tree, maybe inserts it somewhere or something like that. And then the way you derive the semantics here is by, well, expansion of the right-hand side of the non-terminals and by beta reduction. So I think the best way to show this is to give you an example. So let's take this recursion scheme here. And of course, the first step is that you derive A, C. So C is the idea here is that C is a tree constructor that is a one-node tree that is labeled by C, and but A is then a non-terminal that is parameterized in that. So of course this is not a tree. So what you can do is we can replace the capital A by the right-hand side, and then like on a sentential form, you get this here where there's still some substitution to be had. And you can think of this as a tree that has as a root an A, which is a binary tree, and then as the left son this, and as the right son this. And then you can continue to derive, and I'm sorry this is jumping around. So if the left node, the left son of A is X, and X is actually C, well then of course you get the C, and so on. And then you continue, and what you see is, if you keep doing this, basically the upper part of the tree keeps staying the same, and then you can do some sort of limit construction, and then such a recursion scheme actually defines a tree. Or typically, you have to pay a bit attention for some special cases, but let's not worry about this. So the problem then is, the idea with these recursion schemes is that they are, for example, executions or syntax trees or something of functional programs, so where in particular higher order functional programs where functions are passed around as actual arguments and so on. And what you want to do is you want to verify that they have some certain property or do something. And so formally what you do is you take a parity tree automaton, and then you want to know, does the parity tree automaton, well, I assume you know what this is, does the parity tree automaton accept the tree generated by the recursion scheme? And of course, if you have an actual application, you probably don't ask the user to write down a parity automaton. You ask them to write down something in engineer-friendly logic or something like that. So this is this problem, given this recursion scheme and the parity automaton. Does the automaton accept the tree? And this is known to be complete for k-fold exponential time if the order of the recursion scheme is k. And order here means basically how complicated can the arguments to the non-terminals become. So this little, it's a bit unfortunate here with the double dots. So this type dot here is just the type of tree. So you say, okay, as an argument, I give my non-terminal a tree. Yeah, either a concrete tree or something that at some point will be a tree. Or you can have more complicated arguments. You can, for example, have functions that consume a tree and then generate a tree, and you can give this as an argument. Or you have a function that consumes two trees and generates a tree. And so that's still of order 2, but of course you can go arbitrarily high. And of course, the price you pay for this is in the complexity of this problem then. As a remark, so this of course sounds horrible, kx time. In practice, you can often get surprisingly competitive with specialized algorithms. It's not the point of today's talk, but this is actually being used. So in order to explain to you what I want to do, let's have a brief look at, like a very brief look at how you would prove this here. And I'm going to omit lots of things. So you can reduce this to a parity game where one of the players tries to prove that the automaton accepts the tree, and the other player tries to refute that. And note that this is not the acceptance game of the automaton. Yeah? This is a different game, but the acceptance game of the automaton can be found in there. And such a position is then some term generated, or some sentential form generated by the grammar, and an internal state of the automaton. So for example, here we have some non-terminal f that apparently then doesn't have any arguments, and a state q, and ignore the thing in the middle for the time being. And then depending on what the position is, the game proceeds in 3 or actually 4 different fashions. So if the top operator of this on the left side is a grammar non-terminal, you simply unfold it. So assume that in the recursion scheme you have a line like that where you say, okay, f is actually on the right-hand side, this thing here. So then the game would simply replace this to the left here by that, and then nothing interesting happens. But then, for example, in a position like this, the top operator is actually a tree constructor, and then what the game does is it incorporates the acceptance game of the parity tree automaton. So the players, for example, in this case, we would say, okay, maybe the automaton in state q, when reading an A, sends the copy within state q prime to the left and the copy in state q double prime to the right. And then basically you split between the 2 arguments to A, and one of the players, in this case the refuter, or how do you call it, falsifier, chooses where to continue. And then the interesting thing here, really, that's what makes this complicated, is if you have an application like this. So you have H, some non-terminal, and apply to it BF, which is apparently then a tree. So how does this work? Because now you cannot simply expand or so, and of course you could expand H, but then the game would become infinite, yeah, because you can generate infinitely many different terms or so. And an idea you can have is that simply verifier proposes what the semantics, what the results of the game would be on this here, on this argument to the application. And of course there are different things they can propose. For example, could propose that the semantics behave like R, whatever that means, or that they behave like R prime, and such an object is called a residual. And then the other player has 2 options. They either buy this and say, okay, I believe that this is the case, and then the players have agreed that this is actually the semantics of the argument, and you simply continue with the operator side of the application. So you basically, in this you choose I believe or not believe fashion, you can agree on what the argument is, and then the complexity goes out of the way. Or the falsifier can actually challenge this and say, no, I don't believe that the semantics of BF is actually this R, and then the game just continues with this challenge, and the rest of the game is forgotten, and the falsifier tries to challenge this by, well, ignore this, but then they basically propose semantics to that, and then the game continues by verifying whether or not the verifier player has lied when proposing the semantics or not. So this is how this goes, and then of course you also have to deal with variables at some point, but let's not think about this. What makes this complicated is then that, of course, the game can come back up to the top here. Yeah? So this is not a reachability game, it's a real parity game, and basically from every point you can get back to a previously held position simply because, for example, you see here there's the F here, so at some point maybe this will change state to Q and then go to F. And of course, in the other cases, this can happen as well. So keep this in mind. Let me now tell you what I'm actually trying to do here. So the complexity of this problem is complete for k-fold exponential time if the order of the recursion scheme is k. And there is a result by, well, Kobayashi and Ong, that say if you really restrict the parity automaton or restrict the kind of property you can express basically to something that is just disjunctive. Then you go down by 1 exponential. So the problem becomes much easier. And so my question is there actually some middle ground between this? Because, well, this is supposedly expensive, and this here is less expensive, but also you cannot really say that many interesting things. So can we get something that is characterized by space or not by time? And to be honest, the motivation is a mathematician's motivation. I wanted to know, is this true? Yeah, so is there a way to characterize this by space and not by time? But of course, you can also have more practical motivations. You could get more efficient algorithms. I mean, this is a lower complexity class. You go from k-fold exponential time to exponential space with k1 less. But of course, no, I'll say something on the last slide for this. And actually, there was a reviewer who pointed this out. So it's not my idea. But of course, if it helps to identify where exactly the problem becomes complicated. Yeah? Why is this k-fold exponential time? Or k-fold exponential time for k1 less, if you basically have ideas where all the steps on the complexity ladder are. And I think I actually made some progress on this just today. So it was kind of, one would suspect that such a fragment actually exists because there is a connection of this framework of verifying higher order programs to another framework. It's called HFL. This is basically where you shift the higher order things on the specification side from the system side. And there's actually the complexity theoretical ladder is complete. So you have problems that are complete for k-fold exponential time, then for k-fold exponential space, and then for the next time, and so on. And there's a result that connects these two. Actually, you can translate from this system to the recursion scheme system and vice versa. So one would expect that such a fragment exists, but the question is, what does it look like? So what can we do there? And from this, basically from what has been seen before, is that the idea of tail recursion would be very interesting to see here. I would assume you know what tail recursion is at a computer science conference, but let's look at it briefly. So recursive call is tail recursive if it's basically the last thing that happens. And the result of then the function call in which the tail recursive call happens is the result of the tail recursive call. So here are two examples. I think these are the standard examples for explaining tail recursion. So the factorial function and the greatest common divisor. And this one is not tail recursive because the result of the recursive call is multiplied by n. And this one here is tail recursive because it just says return whatever the result of the tail recursive call is. And for example, you see this pretty easily if you just try this with an example. So here, what's factorial of 4? Well, it's 4 times factorial of 3. And well, here, the GCD of 78 and 63 is the GCD of 63 and 15. And then you continue, and you see on the left side, basically the arguments or the pending operations to the result keep piling up. And on the right side, you simply simplify. And the result of this is that. And in programming, tail recursion is quite useful because things like this don't require you to keep a calling context or something like that. Yeah? You just have to remember, OK, I have to pass whatever I compute here back to the original caller, but somebody demanded the answer of that. And in this case, you have to remember, OK, the result of 1 needs to be multiplied by 2, have to go to that, and have to go back to multiplication by 3, and so on. So you can condense the call stack quite a lot. And also, if you want to convert this recursive procedure into an iterative one, for tail recursive programs, it's actually very easy to just convert them into while loops, and sometimes even for loops. So the question now is, where do we find this with the recursion schemes? And well, this is the advantages we had before. So if you're familiar with these things, then you can kind of see it. So recursion scheme of order k, and this parity automaton that gives you a parity game of k-fold exponential size. And if we just could convert this into a reachability game, then, well, reachability is easier than solving a parity game. So we could actually get the result in k-1 X space. So we really want to make a reachability game out of that. Yeah, and this is kind of the same thing as converting this into a for loop. And this is actually known how to do this for parity games. This is called signatures. Basically, to each parity, you associate a number, and then you have a lexicographic ordering of these numbers. And then while the parity game is being played, whenever you see a parity, the respective number is being decreased by 1, and the less important numbers are being reset. And once a player runs out of their, reaches 0 for their parity, they lose. Yeah, so if I'm in charge of the even parities and an even number goes to 0, I lose. So this is actually very easy to convert this parity game into a reachability game. The problem, though, is, of course, this result that reachability games are easy to solve only holds for deterministic reachability games, and these parity games are alternating. So we kind of have to get rid of the alternation in the game. There's a Boolean alternation in the sense that this is actually a 2-player game. We actually want this to be a 0-player game. And there are 2 sources of alternation in this game. So one, of course, is the alternating parity automaton, which has its acceptance game, that is an alternating game, and this handling of the applications. Yeah? And that's why I presented this briefly, this idea that if you get to an application, first one player proposes what the semantics of the operand thing would be, and then the other player can either buy this or not. It's like the fair way how to divide a cake. I divide it, and you choose which side you want. So that's also alternation. Yeah? So one player does this, and the other player has to either takes the challenge or doesn't. And how does it come together? So actually, if we make the recursion scheme tail recursive, whatever that means, then this alternation for the arguments disappears. So look at this picture again. So here we have basically a transition for the parity automaton where you read an A, and then basically the one player decides go left, go right. And then we have this back edge here. And here we have this alternation where the verifier first proposes what the argument should be, and then the falsifier either challenges this or buys this. And this back edge here is the one that needs to go. Because this F here, that appears actually in operand position. So like as an argument to something else. And I would say this is not tail recursive. And the consequence this has is that the semantics of this residual, like of the thing the verifier proposes, that actually depends on the semantics of F, and the game would then link back up. So this edge is really bad. So if we can get rid of these back edges, then such a subgame where the falsifier challenges verifier's proposal, says, no, the semantics of that is something else, I don't believe it, then that really becomes a subgame where you cannot go back. Yeah, because this back edge disappears. So then simply the game condenses to a simpler problem. And then with some tricks, you can get rid of the alternation by simply saying, OK, the verifier decides the semantics should be this or that. And then instead of alternating, like the falsifier having a choice whether to challenge this or not, you simply go into the subgame, solve this in supposedly the space bound you have. And then if the answer is no, verifier lied, then the game ends. And if not, the game can continue here. So instead of the one player choosing, you can solve this game first. And since we don't care about time, we only care about space, this should work. Yeah, because the game then becomes simpler. So this is the idea, to get rid of these this recursion in operand position. That means we don't want free non-terminals there. But of course, this is really not well defined, what I just said. So of course, you cannot simply say non-terminals cannot appear at all in something that looks like an operand position. Yeah, so if you have like a tree constructor and then a few non-terminals below it, that's completely fine. And also, how do I explain this best? So you have to be a bit careful to not overshoot. So clearly, if you go back to this factorial example, the call to the factorial function was not tail recursive because it was a recursive call. But if I just pass around the factorial function for later use, that's not a function call at all. I just pass it around. So if I have functions as first order objects, so that is fine too. And we need to distinguish this. But the framework of the recursion schemes as I presented it really doesn't allow this easily. But what we can do is rewrite them as recursive lambda terms. So this is not my idea, but by Salvatierre and Walukiewicz. So instead of writing it like that, where you have the non-terminals and they have their right-hand sides, you write it as a recursive scheme, or as a recursive term, where you say, okay, I have a recursion on S, well, not a trivial recursion on S, and then S is simply the application of this to that, and these are both recursive predicates. And now you can see what's like an initial use and what's a recursive call. So, for example, this A here, which would be this A here in the recursion scheme side, this is simply the whole term. It simply passes around the function. That's fine. Yeah, this is like completely closed, passing around this function. And this, of course, here just is also not in an operand position. Yeah, it is just under the tree constructor. But this occurrence of B is an argument to the other call of B. That's something you don't want to have. Yeah? This would introduce a back edge in the verification game. So if you recast the terms into this, then you can actually define tail recursion. And we say that a recursion scheme is tail recursive if, when rewritten on the right, like on the right-hand side, no operand side term has free non-terminals. That is some things that are not under the not under such a y something term. And then you can prove that for such recursion schemes, the subgames where the falsifier generates a residual, that these are really self-contained and you can basically solve them before, like individually on their own without having to go back to the other game. So this would eliminate one source of alternation in the problem. The other problem is like the parity automaton is still has alternation. And so we have to restrict that as well. So let's just briefly. So in my framework, transition functions of an alternating parity automaton look like that. So you have a Boolean function here without negation about tuples where the automaton sends their states. Yeah, so this would be for a binary symbol, this would be for a unary symbol, and you can have arbitrary nestings here. For binary symbols, we can actually, and I restrict myself to binary just because it's simpler, we can basically define what non-alternating transitions mean. So we say a transition is branching if it looks like that, where this Q top here is a state that accepts everything. Yeah? So in this case, the verifier chooses either go left with this state or go right with that state. And it would be universal if it's just something like that. Yeah, but just the verifier plays no role in deciding what goes. The falsifier says, we go there and we go there, I choose what happens. And notice that these are kind of dual to each other. And then we call an parity automaton bounded alternation if we can partition the state set into finitely many components such that each of the sets is labeled either as branching or universal. And in a branching set, all the transitions are branching or they go to a set with lower index. So if you want to switch, you have to pay by a descent into a lower component. And the same for the universal sets. And the idea here is that this really characterizes the acceptance game of the automaton then as a bounded alternation game, where if you want to have alternation, you have to basically go back to a set of lesser importance. And think of this as like a weak automata, but now the components are for alternation, not for the acceptance condition. And then you can show that if I want to check a bounded alternation parity automaton against the tail recursive recursion scheme, this can be actually done in k-1x space. And the idea is really that the tail recursion eliminates the one source of alternation, the bounded alternation automata eliminate the other source of alternation, and then you can make it a reachability game. That is bounded alternation, invoke Savage's theorem to get rid of the bounded alternation, and there you are. And so as a remark, this you have to strictly go down. You can relax this a little bit. I didn't present this because of time. So the actual thing is a bit more complicated. I also have an upper bound. I think we'll skip over a lower bound. We'll skip over that. I just show you the result. So this problem is also hard for the k-1 X space. So this is actually a non-trivial construction, but I don't think I have time to show this. So yeah. So what did I do? Introduced this notion of tail recursion to recursion schemes, which I think is really interesting, and also introduced a new automaton model. So this is kind of extends the work of Ong and Kobayashi I cited on one of the first 2 slides. And yeah, found this fragment where we have a complexity that lies between k-1 X time and kx time, which is just what we wanted to do. So there are a few things one could do. So this lambda y presentation is kind of uncommon. And usually, in particular, if you want to have practical model checking algorithms, you do it with other representations. So kind of have to translate this back. And there is some things there that I'm not quite sure how to do. And then what one should look at also is actual model checking algorithms, because right, k-1 space is less than kx time. But of course, this is kind of, in practice, often not the case that space-bounded algorithms are so much better. But actually, there is precedent that for this HFL framework I mentioned earlier, there are advantages if you go to this space-bounded framework in practical terms, just because it's easier to do on-the-fly model checking. And then, I didn't show this, but there is some cleaning up to do with the definition here. So there are some restrictions that can easily be removed, but not in a 15-page paper. Thank you.
Questions?
Okay. Yeah, so this is just more of a clarification question. So there's also like the number of parity colors that you have, right? And does that play a role in this construction?
No, I don't think so. Okay. There's in this Kobayashi-Ong paper I mentioned is they have a result that if you go to just one parity, it doesn't change the complexity at all.
I see. Okay, so the complexity is all on the higher order recursion.
Yes.
And that sort of subsumes the complexity due to
and so I have quite a few papers on things like that, and usually it's the higher order things eat everything else. So.
Okay.
Any other question? I want to ask a question. So if I understood this correctly, this has sufficient conditions, right? That's an example that fits.
No, it characterizes the. It's complete for K for this space complexity class. So there's an upper bound and a lower bound.
But in terms of restrictions, is that the only thing, or is there a chance for other? Because basically, you're saying that you have to do tail recursion and then you deal with the parity automaton. But is it obvious that that's the only, or like is there another inhibitant with the same complexity class, like another restriction?
I think if you want to hit exactly like upper and lower bound, I think this is the way to go. So it's just simply from the analysis of this related framework. And so the idea is that the alternation you really have to get rid of, because alternating exponential space is exponential time of one exponential more. So I don't think there's really a way around this. Maybe you can cast it a little bit differently, but I think in general this is how you have to do it.
And for the theorem statements, you sort of, again, I didn't really understand the details from a short talk, but sometimes there are things which may not be written as tail recursive, but without significant effort be converted to tail recursive.
Yes.
Does this apply to them too, or somebody has to convert? Like the factorial example you showed, that's not a tail recursive, right? But I can change the factorial to take the value in.
Yeah.
And then all of a sudden it becomes tail recursive.
I think you can generally do this, but often, like if you do it in a generic way, you have to go up by an exponential, and then that doesn't help you at all because, well, now it's tail recursive, but one level higher.
Asking about your theorem. The theorem applies says if the horse is like syntactically tail recursive, then
Yeah.
the theorem applies. Not if it's semantically tail recursive. Like if I take something that is tail recursive, but I obfuscate it by.
Well, if you remove the obfuscation, then it would still work, yeah. But, so how do I mean, there is certainly recursion schemes that don't look tail recursive, but with little effort you can make them tail recursive.
Right, but your theorem wouldn't apply to them.
Well, after rewriting, yes. But then there
But
are
rewriting could be very expensive.
yes,
right?
but there should be a general way to rewrite every recursion scheme into a tail recursive one at the cost of one added exponential, which then complexity-wise actually makes it worse.
Right.
Yeah. So, but of course there are some that technically aren't tail recursive, but if you look at it hard enough, then
Right,
this
so
goes.
that's still like classifying those maybe still left open.
Yeah, maybe.
So are you talking about continuations? Like if you use continuations?
Yes.
then you
Yeah,
get
yeah.
rid of one.
Exactly. If you go to the analog of continuation passing style, it's tail recursive, but then it's also very expensive.
Okay, thank you so much. So our next talk is special because it's remote, and I think in the program I press a button and it appears. Yes? Sven? Sven is speaking. Hello, can you hear us? So maybe we should all very
Yes,
loudly
I can hear you. Oh, wait, no, actually. Ari, can you hear me?
Yes, I can hear you. I can see a
Ah.
picture of you, but no slides.
Yes, I will.
Oh, I see now
And
a
then I
video
will
of you,
share
but still no slides.
slides. Just a second. Now?
Yep, we see both you and slides. You don't see us, right?
Sorry?
Or hear us?
Yes, I can hear you.
Okay, so let's start. So our next talk is by Sven, who you see here, and it's parameterized verification of systems with precise 0-1 counter abstraction. Take it away.
Yes, thank you. Good evening, Denver. This is joint work with Paul and with Chana Kennedy. Paul is my PhD student who was supposed to present, but sadly he had a health issue and couldn't join you in Denver. So instead, I will do my best to present his slides. As a very high-level idea of what the talk is about, it's about parameterized verification, which you can think about as verification of systems, component-based systems, regardless of the number of components that run in parallel. And well, 0-1 counter abstraction is our main proof technique, let's say. And what the title doesn't tell you is that it's really the heart of a framework that allows us to capture many of the existing results for systems that have decidable parameterized verification, and also a couple of new systems. Okay, so motivation-wise, of course, we're in an age where even a single processor has multiple cores, dozens of cores actually, or hundreds of cores. And applications might run on multiple processors, so hundreds of processes of any given application might execute concurrently, and then ensuring correctness, so ensuring that certain things will happen or other things will not happen, is very difficult. And this is where we want to use parameterized verification. Taking a step back, what is like the optimal setting for verification is if we have a finite state system represented here with a finite number of states, and we, for example, want to check some specification which might be just reachability of a state or some more complex property. We can give it to we can devise a model checker, and we can give it to the model checker, which can automatically decide whether the specification holds or not, whether the state is reachable or not. This is let's say, easy for a finite state system. But in our setting, we want to have such a process, and then we want to execute maybe 2, maybe 3, or an arbitrary number of processes in parallel. And then we want something like a model checker that tells us whether a specification holds, regardless of the number of copies that execute the program concurrently. This is what's called the parameterized model checking problem. Now, well, as I showed it before, this is not very interesting if the processes just execute in parallel but do not communicate in any way. So usually we consider systems where we have certain labels on the transitions that allow the processes to communicate. I will give you a few more concrete examples later on, but in general, communication between processes, different forms of communication, will be an important point in this talk. Now, when we're talking about parameterized model checking, the problem has long been known to be undecidable, even in case that we have identical finite state machine that all execute the same program. This problem is not decidable in general. So because of that, there are 2 ways out of that. One is we drop decidability. We go to a semi-decision procedure and have something like in software model checking where we don't know whether it will terminate or not. Or, and that is the point of this talk, we want to have a decision procedure. And then there has been a wealth of different results for different types of systems, mostly distinguished by how processes can communicate. And one of the main points of this talk is that while these systems have certain things in common, usually the results that prove decidability of parameterized model checking use completely different proof techniques. And in our work, we find a unified framework that captures the 4 results essentially that we have here on the screen and a couple of others. Okay, so that sets up my talk. And in the rest of the talk, I will first walk you through a couple of these known results that we capture in our framework. Then I'll introduce, on some level of detail, our proof techniques, which allows me to state different problem classes and decidability results. And if there's time, I will talk additionally about an efficiently decidable subclass. All right, so the first model that has been studied in the literature before is lossy broadcast, also known as reconfigurable broadcast networks or mobile ad hoc networks. These are all essentially the same thing. What does it mean? Well, if this is our process template, so every process executes this program essentially, then transitions can be labeled with either a sending action A or a receiving action A. And if a process executes the sending action A, then other processes can receive this A message and can react to it by taking a receiving action A. So in this example, we start with 3 processes in this initial state here. This is how we can represent global states, or we can represent them as vectors. Here in this example, 3 processes are in the initial state, 0 processes are in Q1, and 0 processes are in Q2. This is a very common way for representing these global states. And now, if one process takes the sending action on A and moves here, then at the same time, the other processes that are also in the initial state currently can take the receiving action and can move there. Now, I said can because lossy broadcast means the message might actually not arrive at these processes. So another option is that the sender goes here and only one of the receivers goes to Q2. The other one didn't get the message and stays in the initial state. Or even the sender goes to Q1 and none of the potential receivers actually receives the message. So this is how lossy broadcast works. And these systems have been studied. And the first proof that parameterized model checking, certain parameterized model checking problems are decidable was via a reduction to Petri nets, and actually a later proof for safety properties uses something that is very, very similar to our 0-1 abstraction and was actually one of our inspirations. So moving on to another system model that is actually closely related to lossy broadcast, which is systems communicating through disjunctive guards. So here, a transition can be labeled with a guard that in this case here says exists Q2. So I also like to call them existential guards. Actually, I like that better because the semantics of this is if a process, now here again, we start with 3 processes in the initial state. If a process wants to take a transition that is labeled with such an existential guard that says exists Q2, then this is currently not enabled in this global state because the guard says there must exist another process that is currently in Q2 and that is not satisfied here. But the transition from the initial state to Q2 is actually enabled. So another process could move there, and then the transition with exists Q2 would be enabled, and the process could go there. So this is the semantics of disjunctive guards, and systems with disjunctive guards have also been studied, and decidability of parameterized model checking has been proven, but the proof here is completely different from the Petri net or the 0-1 abstraction proof. It's actually by constructing a static cutoff that only depends on the number of states in the system. And so a cutoff means I have a number of processes that I have to compose, and then I know that I can see every possible behavior of the system, essentially. If I add more processes, nothing new will happen. Okay, so this was 2 types of systems, disjunctive guards and lossy broadcast. I just want to mention a third one, which is just simple synchronization. You might notice just from synchronization of transition systems. Here we also have labels on the transitions. For example, the label A, and the semantics is that all the processes take an A transition at the same time. So if we start in this initial state, for example, 2 processes move up here, 1 process moves down there. They could take either of them, but they have to take one of the A transitions if an A is fired. Okay, and there's a couple of other systems, for example, asynchronous shared memory systems and immediate observation protocols that are somehow related, and we will see that they all fit into our framework, but that have been until now studied separately, and each of them, for each of them, its own proof technique has been developed, and that's like the state of the art. If you have a new system model, you always have to come up with your own proof technique and show that parameterized model checking problem is decidable. Okay, so that covers the known results more or less. Now to our technique. So what is the heart of our technique? It's what we call 0-1 counter abstraction, or simply 0-1 abstraction. So in our example for the lossy broadcast, we have seen a possible step for 3 processes in the initial state. But since we're talking about parameterized systems, there could be any number of processes. So what happens if we have 10 processes? We might, after a couple of steps, end up in this configuration. And the size of these configurations is a priori not bounded, so it might be very expensive to reason about these systems. Now, the idea of 0-1 abstraction is that we don't want to count how many processes are in which state. Instead, we just want to keep track of which local states are occupied and which are not occupied. So here, so it's just a black and white 0-1 thing. Here, the initial state is not occupied, but these other 2 states are occupied. And sorry, yeah. So now to make this a bit more formal, these systems without abstraction can be represented as counter systems. So what I mentioned before, global states can be seen as vectors, which have natural numbers, and the number of positions in the vector is given by the number of local states of our protocol. And the abstraction function that maps this just to zeros and ones takes such a vector and maps it to a vector of Booleans of the same length, where we assign a 1 if there's at least one process in that local state, and we assign a 0 if there's none. So in our example, both of these states with 3 or with 10 processes, their abstraction is the same, and it's 0, 1, 1. So this is the abstraction of both of these states. And then based on such an abstraction function alpha, we can define a 0-1 counter system, which is defined in the standard way, an abstract transition system based on such an abstraction function. So our global states are now these Boolean vectors, and there is a transition between two abstract states whenever there is a transition between the concrete states in the concrete system. This is like a standard definition of an abstract transition system. And now we're interested in cases where this 0-1 abstraction is precise in the following way. We want to have that a global state given by a vector v is reachable in the original system if and only if its abstraction, alpha of v, is reachable in the abstraction, the 0-1 counter system. Now, in order to identify for which systems 0-1 abstraction is precise, we use tools that are already known in parameterized verification. In particular, we use a well quasi-order. Well quasi-orders are known from well-structured transition systems where you have a well quasi-order and you have to show that your transition relation is fits the well quasi-order, so to say. I will explain in more detail later on what it means. And there is like a standard well quasi-order that says, well, a global state v is smaller than a global state v prime if and only if for every position of the vector, the number in that position in v is smaller than the number in v prime. So the number of processes in a local state is bigger in v than in v prime for every local state. And we refined that well quasi-order. An example or a couple of examples would be here with the standard well quasi-order. 0-1-0 is smaller than 0-42-0 because every position is smaller. 0-1-0 is also smaller than 0-42-1, but 1-0-0 is not smaller than 0-42-1 because in the first position, this first one is bigger than the second one, so it doesn't fit. Okay, so we refined that well quasi-order for our systems. For the 0-1 abstraction, it turns out that this is an important well quasi-order, where in addition to what was necessary before, we require that the two vectors agree on the positions where we have zeros. So the empty locations where no process is need to be the same. So with the same examples, now 0-1-0 is still smaller with respect to our new well quasi-order than 0-42-0 because they agree on the positions where they have zeros, and in the other position, 42 is bigger than 1. But the second case doesn't hold anymore because now we have a 0 in the third place on the left and a 1 in the third place on the right. So these two are not comparable. And the last one is also not comparable like in the first case. In this case, for multiple reasons. We don't agree on the zeros, and we're bigger here than we're here. Okay, so we have this new well quasi-order. And I said this is necessary or helps us to identify when the 0-1 abstraction is precise. And this brings me to our first result that says, if a counter system, C, so the non-abstracted one, is compatible with this 0-1 well quasi-order, and in our case, we need it to be forward and backward compatible, then C has precise 0-1 abstraction, so then we can use the 0-1 abstraction to check reachability, and it will be precise. We get an if and only if relation. So I didn't explain yet what compatibility means. So let me do that. Compatibility with a well quasi-order means if we have a global state V and a transition to a global state V prime, and we have another global state W, which is bigger than V with respect to our well quasi-order, then there must exist a transition to a W prime from this W such that W prime is again bigger in the well quasi-order. This is forward compatibility because we took a step forward. And backward compatibility is what you would expect. So we start with V and V prime again, and we have something, a W prime that is bigger than V prime. And now we need to be able to go backward. We need to show, or we need to guarantee that there exists a transition from some W to W prime, where W is, again, greater than V in our well quasi-order. So this is compatibility with respect to our well quasi-order now. And we need to prove this for all possible actions in all configurations of the system. And actually, we can prove that for all the types of systems that I talked about so far. So for lossy broadcast, disjunctive guards, synchronization, all of them have steps that are compatible with this well quasi-order. And now, what does it mean? Based on the lemma that I already showed you before, this means, well, if we wanted to do parameterized model checking for such a system, if we want to do it in a naive way, we would construct a counter system which has an infinite state space, so checking reachability might not be decidable. But if we can show that they're compatible with this well quasi-order, we know that the abstraction to the 0-1 counter system is precise, and then we can check reachability of the abstraction of the state that we're interested in the 0-1 counter system. And this is, the abstraction is a finite system, so this reachability check is decidable. So that's what we get for all of these systems, just by identifying this relation between the well quasi-order, the 0-1 well quasi-order, and the 0-1 abstraction of the transition system. But I said in the beginning, model checking we might be interested in more complex properties, so we can also cover that. An example is coverability of relation. We just might want to say, well, the number of processes in some state QF that we're interested in should be greater or equal to 1. Can we reach a state where this holds?
Hello, can you hear us?
And we also can have a separate control process, which is essentially supported in the 0-1 abstraction without additional cost, which is not true for all of the existing results for the systems that I showed you before. And then the cardinality reachability problem is for an input C, a counter system, and a cardinality constraint out of this grammar, decide whether C can reach a configuration that satisfies the constraint. And then what we get is our main result if the counter system is compatible with our well quasi-order and a small side condition that it is a polynomial polynomially abstractable, which essentially means we can get the abstract counter system at polynomial cost from the description of the original system, then the cardinality reachability problem is decidable and it's in p-space. And the proof is not difficult given what we have already seen. Essentially, since p-space is the same as non-deterministic p-space, we can guess a path in the abstract system, and then we can just check it. Okay, so that's nice. For all systems that are compatible with our well quasi-order and satisfy a small side condition that is also satisfied by all the systems that I showed you, we get decidability of this problem, this more complex problem in p-space. And actually, we can also show that the CRP for this class of systems, even if we restrict it to systems without a controller and with only literals of the form the number of processes in a state should be greater than 1, is already p-space hard. Okay, so it seems I need to speed up a little bit. So this is already a really nice result, I think. It captures a lot of existing models and generalizes the results for these models somewhat, but not too much. But now we can actually go beyond these existing models. So we've seen, for example, lossy broadcast and disjunctive guards or existential guards. We can actually mix them in the same process template, and it will still fall into our fragments. That is one of the easy corollaries that we can get. I already mentioned we can also have a controller process, so only one process will execute this process template, and an arbitrary number will execute this process template. And we can go beyond that. We identified a new communication primitive, which we call guarded synchronization. So we have these synchronization actions that we had before, but now we can actually guard them both with existential and with universal guards. So the idea of the semantics is this B transition can only be taken if there exists another process in Q2, and if all processes are either in Q1, Q2, or C1. So no process can be in one of the initial states or in Q3. And this is kind of surprising because it's known that with individual transitions with guards, this would lead to undecidability, but we can add it to the synchronization steps, and we can even mix it with everything we've seen before, and it will still stay decidable. Okay, so guard synchronization steps are compatible with the well quasi-order, and also mixing these things in one template also works. Okay, so to summarize this part, and actually, let me just go to the conclusion. So I'll just say one sentence about improving this. So we inspired by existing results that for some of these models, the problem is decidable with lower complexity. We also identified a subclass of our systems in which we match the complexity results that we get from this previous work. And it's essentially based on this additional condition. You can look it up in the paper if you're interested. And it holds, for example, for lossy broadcast and disjunctive guards. Okay, so let me wrap up. We looked at the parameterized model checking problem for different types of systems and unified them into a framework that is based on compatibility with the 0-1 well quasi-order. And if we can prove that compatibility, then we can check cardinality constraint reachability in the abstract system in the 0-1 abstraction. And this holds for many known communication primitives, their combinations, and new communication primitives. And even with a controller process, the cardinality reachability problem is decidable in p-space. If you're interested in details, you can find it in the proceedings or in our archive paper. And with that, I'd like to conclude. Thank you very much.
Thank you. Can you hear us?
Yes.
Okay, great. Do we have questions?
Yes, we do.
Hi, Sven. This is Kedar. That was a great talk. So I was, this is a really nice generalization. I guess my question, which is sort of a natural one, is can you go beyond reachability, like to, linear temporal properties, eventuality, that kind of thing? So it seems like, this probably breaks down at some point. Do you have an idea of where it does? Because some of the earlier results you quoted, they also, I think, can handle some amount of linear time properties.
Yeah, this is true. So for the lossy broadcast and for the disjunctive systems, there are also results for Leibniz properties. But we have an example in our paper that for Leibniz properties in general, the 0-1 abstraction does not work. So you would have to invest additional work to get Leibniz properties, to decipher Leibniz properties. We have looked at it, but it's work in progress. We don't have results. But I mean, we have other results that build on the idea. So we had a paper in formal methods last year where we use 0-1 abstraction in the context of deciding threshold automata, and we have an archive paper where we use implicitly at least 0-1 abstraction on networks of timed automata that communicate by lossy broadcast or disjunctive guards.
Okay, thank you. Any other questions? All right, so I had a tiny question. Can you comment, is there a relationship between this and finite model property? Because like some of the results you mentioned, decidable by reducing to a finite model, like does that also carry now to other systems, or is that just completely unrelated?
Yeah, I mean, implicitly, I think, well, not implicitly, I think it would allow you to compute a cutoff also. I haven't thought about it, so I'm just making this up, but
I wonder.
I think there is a connection.
So you don't think that there are systems for which there are no finite model property, but the 0-1 abstraction is complete?
Say again?
So you're saying probably there aren't no systems for which there is no finite model property, but 0-1 abstraction is complete?
There are definitely systems for which 0-1 abstraction is not complete or not precise. But I mean, the other way around, if a system has 0-1 abstraction, then I think you can get a finite model property out of that, yeah.
Okay. I mean, because there are decidable parameterized systems for which there is no finite model property.
Mm-hmm.
Right?
Yeah,
like you do
that's
something
true.
Slightly different, like interference of some kind. Thank you.
Yeah, definitely. Thank you.
Thank you so much. Sorry that you couldn't be here.
Yeah. Okay, bye-bye.
And this is the last talk of the session. This is property agnostic base case extension for scalable verification of distributed systems. And I think Kyle Story is giving the talk.
There we go. Nice, excellent. Cool. So I'm a big fan of model checking. Model checking is just very helpful to, when you're given a distributed system, you can very easily define the system almost exactly as is given you in the model checker. You can write out your LTL properties to define what things you want to know are true in the model checker. And it's very efficient, very good for verifying safety and liveness properties. However, it only really works on a small system. If you have a large number, it gets computationally complex, it chokes on you. On the other hand, we have theorem provers. You get to use pretty much all of math. The world is your oyster. And you can prove arbitrary things. You can use inductive reasoning to prove properties about arbitrarily large systems. However, getting safety properties and especially liveness properties to prove out in these systems is really, really difficult. So you can see how these pros and cons of these two tools kind of are duals of each other, and if we could combine them, maybe we could get the best of both worlds. So that's what we're going to try and do in hopefully a unique way. And the way what we're going to use as a case study to try this is a system called MyChips. And MyChips is a kind of digital currency, and the way that you can start to think about MyChips is to begin thinking about a barter that involves more than two people. So for instance, Bob, his car broke down. He really needs it fixed. And Cindy is able to fix his car, but she would really like a well dug on her property. It's a lot of work, but John's willing to do that work. But John needs solar panels installed on his house, which happens to be what Bob can do. So you can see if they got together, they could do each other's work and everyone would be happy. So how can we facilitate this exchange? So traditionally, what would happen is Bob, he's up a tree. He really needs his car fixed. He's going to go to the bank. He's going to take out a loan and get some cash. Bob will use that cash to pay Cindy, who will fix the car. Cindy will use that same cash to pay John to dig the well, and John will give that same cash back to Bob in order to install the solar panels. At which point Bob can take it back to the bank, and the bank says, great, but you owe us a little bit of interest. So the question is, can we facilitate this trade without the need for this bank? And the way the MyChip system works is using a series of IOUs. So rather than paying each other directly, we write these IOUs that put all these people in debt to each other. And they just do that as they're needing to make their transactions. And what MyChips does is identify these cycles of debt and arranges so that each person will forgive their successor's debt in exchange for having their predecessor forgive their own debt. So that's kind of what the MyChip system is doing. And that process of forgiving each other's debt, they call a credit lift. And that's the piece that we want to verify. So to get a little bit of understanding of how a credit lift works, we'll just give an example. So the credit lift protocol operates in 3 phases. The first is discovery, where we're identifying the cycle of debt. That's really hard, and there's no value being exchanged. So we set that aside, and the other 2 phases we're going to verify. So the second phase is the promise phase, and the third phase is the commit phase, and we'll see that here. So there are 3 different types of entities that participate in this credit lift. The first is the originator, who is just any member in that cycle of debt who wants to start the process. Then there's any number of relay nodes. These are other members that are in that cycle of debt. And then there's a third special node, this referee. And the referee serves to ensure that all the nodes reach a consensus on whether to forgive the debt or to roll back. So for example, the originator, they want to initiate this process and they're going to send a promise to relay 1. That promise is going to have 3 pieces to it, 3 core pieces. The value that's going to be forgiven, they're also going to specify some timestamp in the future, by which point if we haven't all promised, we're going to roll back and the promise will be invalid. And then the third is specifying the referee. And this promise serves as a contract between the originator and relay 1 that is made valid when you receive the digital signature of the referee. Cool. So the relay 1 will receive that promise, consider whether they trust the referee to be fair when deciding, and if they like the terms, they'll forward it. Followed by the next relay, and in this case relay 2 is the last one, will send its promise back to the originator. And the originator has seen this promise has come around the cycle, and they believe that everyone's now agreed. At which point, the originator will reach out to the referee, say, hey, I'd like to commit on this lift. And the referee will look at its own time and say, is my timestamp before the given timestamp for this lift? If it is, they'll provide their digital signature. And in this case, they do provide their signature verifying that it's been completed. So at this point, the originator has a promise from relay 2 to forgive its debt. So it's motivated to send the signature to relay 2 to make good on that promise. At which point, relay 2 is also motivated, but has a problem. It experiences an error and crashes. So it's not able to forward that signature to relay 1. And relay 1 has received the promise, and according to its own clock, it's well past the timestamp limit. So it's left in limbo. It needs to know what to do. And what it can do is it can reach out to the referee and say, hey, what's the status of this lift? At which point the referee can look in its records and say, oh yes, I know this lift. Here is the signature. So you can see that all the active nodes are able to reach a consensus that we're supposed to forgive each other's debt. And relay 2, if it were ever to become active again, it could also reach out to the referee to find the status. So that's how we're reaching a consensus. So this MyChips protocol, it's defined using a state machine, and it's fairly straightforward to implement it as a Mealy machine model that we can put into our model checker, which we use to spin. I don't want to get into too much detail here, but suffice it to say it's fairly easy to implement in spin. The question is, how can we verify a system that's arbitrarily large? Spin can verify 1, 2, maybe 5 before it starts to choke, but how can we do an arbitrarily large system? It's one with any number of relay nodes. So to do that, we're going to turn to our theorem prover, and as a basis for that, a theoretical basis, we're going to use trace theory. The trace theory was introduced by Dill some 35 years ago in the context of electronic circuits. And what he considered is, when is it safe to substitute one electronic component for another? And the way he went about doing that is considering traces. So for instance, this electronic circuit, you might see the input A change, followed by the input C changing. This is all feasible. Followed by the output F changing, and then the output E changing. That's a possible trace of this electronic circuit. However, if we look and see A change followed immediately by a change on F, just because the way this module is wired, that's not feasible, it's not possible. So what Dill said is, let's just consider these modules as black boxes and only consider the possible traces of inputs and outputs that could happen. Cool. So with that idea of like, when is it a safe substitution, how can we use that to prove these properties for an arbitrarily large system? So the way that we're going to do it, we start with a small system that we can verify in spin and prove the properties on, with just one originator, one relay node, and one referee, the smallest possible system. And then we're going to look at the relay node and put a black box around that and consider what could fill this role. Now, of course, a relay node could fill this role, but the question is, can we put in here a chain of n relay nodes and have it fill this role, be a safe substitution? And if we can prove that, then we can say that for a large system, the properties we proved on the small, because it's a safe substitution, the properties continue to hold. So that's the approach. Now, it turns out it's very difficult to prove this directly in the Mealy machine model. It's very tricky to prove. So what we're going to do is we're going to use a different representation. So we're going to use a partial order representation that's essentially just a series of rules that define the input and outputs and the traces of events that we could see. Cool. Sorry, I'm a bit lost. Okay. So, I think I got my slides misordered. Where am I? Okay. So, for an intuition of how this proof is going to work, we're going to start with our base system that we are able to verify using our model checker. We'll prove all the properties we're interested in. Then what we're going to do is, Okay. Then what we're going to do is take our relay node. I'm going to go back. I'm sorry. Okay, so there are 3 core lemmas that we're going to need to be able to prove this inductive proof. The first is the base case, which we can prove with our model checking. The second is conformance equivalence of a chain of n plus 1 relay nodes to n relay nodes using our partial order definition. In our math, we use this B for black box. It's our black box definition. And then the third piece we're going to use is conformance equivalence of our black box definition to our original Mealy machine definition. So if we have these three things as lemmas, we can show that the properties we care about extend to an arbitrarily large system. All right, so to start, we have our base system, which we've proven our properties on that we care about. Then we're going to use our lemma 3 to show that it's a safe substitution to replace our relay node with our partial order definition of our relay node. Then we're going to use our lemma 2 to show that a chain of 2 of these partial order definitions of the relay node is a safe substitution. And we know if that's a safe substitution, the properties continue to hold for the system. Finally, we're going to use our lemma 3 one last time to convert us back to the Mealy machine model. And that's our inductive step on our proof. Okay, so this is a lot of things to believe. But if we can show these three lemmas are true, then that gives us all we need to prove that the system continues to hold, the properties hold as the system grows large. So the first case is fairly straightforward to implement in Spin. I don't want to go into too much detail, but there are 4 properties that we cared to verify. The first is that we are not left in limbo hanging forever, that we eventually get out of the pen state for all of the nodes. The second is that if any of us believe that the lift has committed and we've forgiven debt, then everyone believes that the lift is forgiven. Third, we say that always eventually we're going to, we're saying that nobody's harmed. Their balance, the change, the amount of debt they've forgiven versus the amount of debt they have, is typically 0, but we do allow for it to be greater than 0 in cases where some nodes go inactive. And then last, we say that for all active pairs of nodes, they agree on their change of balance. So these are the 4 properties we care about and we prove. And in our model checker, we can very quickly evaluate that. It takes some 16,000 states, 172,000 edges, and on my machine, it took 10.5 seconds to prove that. So that proves our first lemma. So we'll move on to the next, this conformance. So the idea that a larger, more complex system can conform to and be a safe substitution for a smaller system can be unintuitive. But what makes this possible is this idea of projection. And the idea is that if we have, it essentially boils down to hiding the internal details, the complexity of the internal of this component. So if we have a system, for example, that has a chain of 3 relay nodes, we have 0, 1, and 2 in here, and we want to consider whether it's a safe substitution for 2 relay nodes, what Dill's work allows us to do is through a series of renaming and hiding things, we can reduce the alphabet of events of the larger system onto the smaller system and essentially just remove those events. You can look at Dill's work for how that works. But that's what makes it possible for this larger, more complex system to conform to the simpler system. But that doesn't solve everything. What we still need to be able to prove is that that projection doesn't change our partial order rules, that our partial order survives that projection. Now, this can be pretty tricky, and it really shows the power of our interactive theorem prover I used, Coq. There's a lot of edge cases that are really tricky, and it is able to enumerate all of those cases and force me to deal with them. Now, the first 7 are fairly straightforward to prove. The last one is the most difficult. This all receives causal. This is the idea that if you've received a message, it must have already been sent. And you can imagine that if you have a system with, say, 3 nodes, you have node 2 sends a message to the originator, node 0, right? So node 0 has received a message, but when we project the system, that send from node 2 gets projected out and gets lost. So it appears that this node 0 received a message and it wasn't causal. However, we can show that for all valid system, there exists a node 1, in this case, node 1, that sends a message that would have gone to node 2 that can wrap around. So there's some tricky cases. It shows the power of our theorem prover that we can look at each of them individually and check them out. You don't have to trust me. You can go and check the source code. It's a machine-checked proof. For some road markers along the way, the top-level proof is larger conforms to smaller, and we write it in this way. It's for all traces, it's an ordered list of actions. If that trace is valid for a system of size n plus 1, and n is greater than 1, then that implies that when you project that trace onto size n, it's valid for size n. And this is not quite exactly what we're looking for as far as what Dill would have written for it, but there's a theorem in the paper that shows that this property implies the conformance that we care about. So our theorem prover, it's not a pretty proof, but it is machine checked. It's 24 lemmas and theorems. It's almost 2,000 lines of code, and it takes about 8 seconds for that proof script to verify.
So you're missing one more time.
Hmm?
How long did it take you to write it?
That's a very long time. We're talking months, probably 9+ months to write it. So it's very difficult. It's manual effort for sure. Cool. So that's our second piece, this conformance of n plus 1 relay nodes to n in this black box model, but we still have to show we did this representation change. We need to show that that representation change was a safe substitution. So we can do that using conformance equivalence, saying one is a safe substitution for the other and vice versa. So we can take this and do a few simplifications. First, the alphabet of events for a single relay node is the same, whether it's using our partial order definition or using the Mealy machine, so we can just drop the projection, they're equivalent. And we can consider the possible traces of events in our black box model versus the possible traces of events in the Mealy machine model. And we need to consider both sides of this disjunction, and we can do one at a time. So this side, we say that all the possible traces in our Mealy machine model is a subset of the possible traces in the partial order, right? So with a little bit of Boolean algebra, we can show that this is the same as saying there does not exist a trace that violates the validity rules, the partial order, right? Which happens to be something that a model checker is very good at checking for us. I'm a big fan of model checking, and we go ahead and do that. And it takes a little bit longer as far as computational goes, but 24 seconds, we're able to prove that there doesn't exist a trace that violates these partial order rules. So that gives us this half of the disjunction. We still have one left, and I'll tell you that this we've satisfied to our satisfaction, but it's not quite the same level of rigor as the others. So we're trying to say that the partial order is a subset of the possible traces of the Mealy machine. Now, we consider the traces of events that are possible in the partial order. And this trace of events is actually infinitely large. There's some cycles where a node can reach out to the referee, and the referee says, oh, actually, we don't have a signature yet, but we haven't reached the time limit yet, so just pend, ask again later, and this could potentially happen an infinite number of times. That's a loop, right? So this set is infinitely large, so we can't evaluate every single one, but this MyChip system is designed to be idempotent. So if you receive a message once, you reach the same state whether you received it once or multiple times. So what we can do is divide all the set of traces into equivalence classes and then pick a canonical member of that class where each trace has each type of message at most once. So we can break that up. There's 9 equivalence classes that we've identified. And the question is, are these equivalence classes present in our Mealy machine model? Which again, I turn to model checking for that. Now, for these 9 cases, we considered each of them. They're very quickly discovered, some more quickly than others. And to find a witness trace for each of these equivalence classes, it took our model checker some 28 seconds. Cool. So that proves the first one, the second one, and the third one with, we have high assurance that this third lemma is true. So given that, that shows that our inductive argument, we have our base case, we have our inductive step that shows that the properties we care about extend to an arbitrarily large size. Cool. So we extended the model checking results using an inductive proof. And we did that using Dill's trace theory and conformance in two unique ways. The first is to prove the inductive step, and then the second is to transition between two different representations of the system, show that's a safe substitution. What's really nice about this method is you can prove any properties you want using model checking, and we don't need to know about them for our inductive proof. The inductive proof doesn't consider what properties we've proven, which means that if there's anything else we'd like to prove extend to this large system, all we have to do is check our small system, and we've shown that the properties continue to hold. So that's a really nice feature. And I'd just like to say that for the 4 properties we looked at, given some assumptions that in the MyChip system, those 4 properties hold for an arbitrarily large number of participating nodes. That's that. Yeah.
So right. So for the very interesting presentation and very interesting combination, by the way. For the third property, the third part of your proof you had, why do you need to establish both directions? Maybe for safety properties, one of the directions is enough, right?
Yeah. So that is unknown, right? It's like, it seems like maybe we don't need it, but how can we prove that we don't need it? So maybe there's a weaker kind of equivalence that we could have that's maybe not this conformance equivalence that would be sufficient, right?
I mean, so typically for an abstraction would be enough for safety property, right?
Mm-hmm.
So if you check the safety property on the abstraction, you're okay.
Mm-hmm.
So I would think R less than, or R in your partial order less than equal to B should be enough for, at least for safety. Maybe not for other kinds of properties, but okay.
Right, yeah, that's a good point.
So here, so for the last conformance equivalence, you consider the inclusion of the traces, right?
Mm-hmm.
So is there any situation that you need to consider like a stronger conformance equivalence? Not only the traces, but probably for every several steps you need to be seen.
Yeah, so that's a good question. So the idea, I think it comes down with what Dill's work is giving for us, is that by showing that the possible set of traces is a subset, that's just allowing us to show that it's a safe substitution. Really, we're not considering the properties for that case. It's just a means for showing that we can substitute this larger system.
I see.
Does that answer your question?
Yes, but what I'm thinking about is it possible that your system behavior can be so complicated such that you only require the inclusion of the trajectories cannot really guarantee the safety or guarantee the similarity?
I suppose there are some things, like for instance, timing, right? If you're timing reliant, then this is not going to work for you.
I see, yes.
There might be other properties,
exactly.
right?
Yes, thank you.
Any other questions? All right, well, let's hang goes figure. There's a half an hour break now. We're back.
1, 2. Does it work?
Yeah.
Good. Excellent.
Okay. It's time, so let's start. So the first talk of this session is called Expect All, a BDD-based approach for link failure resilience in elastic optical networks, and it's going to be given by Jiri Serba from Aalborg University.
Okay. Thank you very much for the introduction. And Expect All, yeah, that's the name of the tool and approach I'm going to present for failure resilience in elastic optical networks. Okay, now it's working. So the whole paper is motivated by a growing demand on higher bandwidth and shorter latency in computer networks. And in a fully optical networks, we eliminate one of the bottlenecks, and this is the conversion from optical to digital signal at every router. And that defines the so-called routing and spectrum assignment problem that I'm going to discuss today. And the idea is you need to find the light path and assign the frequency slots through the whole network. And in particular, in case of link failures, we need to quickly improvise and find an alternative path that avoids the failed links. And according to the technical specification, this should be done in less than 50 milliseconds. And in the worst case, 200 milliseconds. And then what we suggest is an approach based on binary decision diagrams that will find not only one solution, but in fact all solutions, including the optimal ones to this problem. And I will show you how we do it. So the routing and spectrum allocation problem is that we assume we have a number of traffic demands that transmit data across the light path. And for every light path, we need to find a route and allocate the frequency slot that satisfies three conditions. So first, it has to be continuous. So we have to use the same frequency slots along the whole path. It has to be non-overlapping, which means that if I have two different light paths and they share the same link, they cannot share any of the frequency slots. And finally, it has to be contiguous, which means that if you need 10 slots, for the size of the demand, they have to follow each other. You cannot make gaps in between. So here is an example how a possible allocation can look like. And then we need to implement the fast failover. So links can and will fail due to different reasons. And we would like to quickly reconfigure the system. And the important things is that, first of all, correctness. So we have to reconfigure it to satisfy all the three conditions. It has to be fast, less than 50 milliseconds. We would also like to do it in a resource efficient or optimal way, because some of the configurations are better for future arriving demands than others. And possibly we would also let the operator to choose. So offer a number of solutions. For example, they might want to minimize the number of light paths that need to be reconfigured in case of a link failure. And the classical solution to this is over-allocate the spectrum. So for every... Let me try it here. I think it broke. Okay, does it still work? Yeah, good. So we can over-allocate. So that means for every primary path, we allocate also the spectrum for the secondary path. We can be a little bit smart that some of these can be shared. And this is very fast because we already allocated the spectrum. We are resilient to one link failures, but we waste lots of resources because they could be used for some other light path. And we would like to find some optimal resilience, not only for one link failure, but for arbitrary number of failing links. So a classical solution that was already presented in the literature is to use integer linear programming to solve the RSA problem. So I'm not going to details, but we implemented some of these classical solutions that we found in the literature to see how fast they can actually be. And then we evaluated on some small, medium-sized network topology, Deutsche Telekom and Cantor. And we generated some demands based on a gravity model and a real population size, and measured how much time does it take to compute a new solution or optimal solution. And as you can see, with the increasing number of link failures on the x-axis and the time needed on the y-axis, we need seconds. So this is definitely not going to allow us 50 millisecond reconfiguration time, in particular if we go to larger networks and more demands. So attempt number one would be, well, let's pre-compute it. So let's prepare for all the failure scenarios, but as you might expect, this is exploding in the number of links you will prepare yourself for. So we tried for a number of demands. If it's for one failure, you can prepare yourself in 3 minutes and then you can react immediately because you already know which path to use. For 2 link failures, 3 link failures, this starts taking hours, and with 4 and 5, this takes days and weeks to compute. So again, that solution does not scale. So the challenge is we would like to be resilient to arbitrary number of link failures, find optimal resource allocation, and be fast. So let me a little bit formally define the problem now. So in the RSA problem, we are given a number of demands. Each of them have a size. Let's say in my example, the size is just 1. For every demand, I have defined some path that I'm allowed to choose from when I want to shoot the light through the network. And depending actually how long is the path, you have to use different modulations, and some of them will require more frequency slots than others. So in my example, the path pi1 and pi3 has 3 hops, and that requires modulation that needs 2 frequency slots, whereas the short path, they only need 1. And then we have a number of frequency slots. Usually that's more than 300, but in my example, it's just 1 and 2. And then we can define the channels. These are all the contiguous slots that we can use. So they are just 3 possible channels I can use. And now I would like to say what is a solution. And solution is an assignment from every demand to the path that I choose, and also to some of the channels that are here. So for example, the solution that is highlighted over there is I choose the pi0 and pi2 for the demand 1 and 2. And let's say both of the demands, they use the channel 1. It's a short path, so according to the modulation, this is fine. And this is actually an optimal solution. And optimal in the sense that it minimizes the highest used frequency slot, because we would like to keep everything packed together in the beginning, so we are ready for the demands that come in the future. Is another solution. I can keep the path pi0, but the second demand will take the path, the 3-hop path. In this case, I have to use a different channel because it's a longer path, so I will use 2 slots, 1 and 2. And that's again a correct solution, however, not optimal anymore because the highest frequency slot is now 2. So now the failover problem is that I assume I have some set of failing edges, E fail, or size at most k, and I want to find a solution, the path and spectrum assignment that avoids such that every path intersection with the failing edges is an empty set. So that's pretty simple problem. And now when links fail, for example, if V2 and V6 link is not available anymore, we don't have this as a solution as you would expect, and suddenly this is now an optimal solution because you cannot find a better one. And the task is to find this fast. So in expect all, we compactly encode not just one but all solutions to the RSA problem. And then we can quickly find a solution because it's already pre-computed. We use binary decision diagrams for that purpose. So binary decision diagrams is a data structure that allows compactly represent Boolean functions. It's a rooted acyclic graph. There are two terminal leaf nodes, true and false. Usually the false is not shown and all the edges that go there are omitted, like in my example. And every node has a label of a Boolean variable. And typically two outgoing edges, the high and low edge. High means we set the variable to true, low means we set it to false. And then when you have a pass from the root to the terminal node 1, this actually gives you a satisfying assignment or the, that is represented by the BDD.
Sorry.
I think it's better now. I made a note. Good. So how do we do the encoding? We need to define the Boolean variables, and so for every channel, we will have for every demand we will have the encoding of channels, and we only need log 2 of the number of channels Boolean variables for that. And for every pass that is in the D pass of the demand, we also need some variables to encode that. And the whole solution is encoded that, you know, for every demand we have the path encoding and the channel encoding. So first we can define a BDD which is defining the assignment. So I say that for every demand D, I have a disjunction over all paths that is available to take, and then I have encoding that, you know, that path is encoding in the variables of that demand. And there is some fixed encoding scheme that I assume is sort of defined implicitly. And then I say that now there is an OR, and then for all channels that can be on that demand and that have the proper size, that means the modulation times the size of the demand, they have to encode, they have to be encoded in the BDD. So as an example, in my running example, when I do the assignment BDD, it looks like this. And here is the encoding that I used. So first the path. Here I only need 1 bit for encoding the path. Each of them has just 2 options. So this is 1, 1, which corresponds to pi 1, pi 3. And then I have 2 bits that encode the channel of the first demand, which in my case is 0, 0, 1. And 0, 1, this is the channel 1, 2. And then the other one is also 0, 1. That's also channel 1, 2. So that path encodes this concrete assignment. As you can see, I'm already breaking the non-overlapping condition here, so I need to intersect this BDD with the one that actually guarantees that these properties hold. And it's the no-clash BDD, which looks like this. And it says that for all demands and all paths in those demands that actually intersect, either these 2 demands are not scheduled to take this path, or if they are, then for any channels that actually have some common slots, they cannot be encoded in both demands. So that's how it works. And when I build this no-clash BDD, it looks like this. And it encodes all the bad assignments that are clashing. Well, it encodes all the good ones. There is actually only one that is clashing. And you see there is this one long path that actually goes to the node 0 that I omitted. And that's the assignment which takes pi 1 and pi 3, and then 0, 1, 0, 1, which is this 1, 2. And that's the clashing assignment that is now excluded in the BDD. And then what do? We simply take intersection of these BDDs because they are closed under the operation, and we get the RSA all BDD, which encodes all the correct assignments. So this is an example of that intersection of these 2, and this is what it looks like. And when I keep it here and I go to my example, I can, for example, see how the solution 1 is encoded. So solution 1 should be the path pi 0, which is 0. That's this. The other is pi2, which is 0, so we are getting here. Here you can see that the first bit of the first channel is skipped, so actually it can be 0 or 1, and the second one has to be 0. So in fact, this encodes that either the channel assignment can be 1 or 2. And the same, the first bit of the second is skipped, so the second bit also says it has to be 0, so it can be the channel 1 or 2. So this path actually encodes 4 different solutions, including the one that I depicted in my running example. Okay, so now we can build the BDD. All the solutions are there. We would like to extract the optimal ones, those that actually minimize the highest used slot. And it's done by a small trick. So we introduce some new Boolean variables, depending what is the maximum number of slots we have. And to the RSA, we conjunct that for every demand over all channels, if we encode that channel on that demand, then we have to set all the variables SF that are smaller than the maximum slot in that channel. We have to set them to true. And now the question is simply, what is the smallest BDD like that has a solution and some of the SF is false? Let's find the smallest slot that we can set this variable to false and it still has a solution. And we can do some binary search and relatively quickly find the optimal solution in this way. Okay, so now we could be already done. We know how to construct the BDD. We know how to get all the optimal solutions, but we would like to speed it up. So sometimes there are some redundant solutions that we are actually not interested in. And this may result in a huge construction time of those BDDs. And we suggest 3 techniques how we can reduce it. So first, we can actually compute the sum over all demands, what is the maximum number of slots they need, and we simply limit the number of slots to this maximum value. Because we know if there is a solution, there will be also a solution that doesn't use more than that many slots. So instead of exploring this huge state space, we just limit it to 9 in this case, and we know the solution will be there. So that's pretty simple technique. We introduced another that is called gap-free restriction. And the idea is that in the optimal solution, we assume that every demand must either start in the lowest slot, slot 1, or if it's not possible, it has to directly follow after another demand that overlaps with it at least on one edge. So for example, this is not a gap-free solution, but this is the only demands that actually overlap is D2 and D3, but all the others, they have to start on slot 1, and then I have to order these in one way or another. So again, that's a safe restriction. It preserves all the optimal solutions and allows us to speed it up. There is a way how you encode it into BDD. We also have yet another restrictions that remove symmetries, because we don't really care whether the demands are ordered like this or like that. These are symmetric solutions, so we simply impose some ordering on the demands and say that first we start from D1 and then D2, and there is a formula that guarantees that the ordering is kept. This is not completely safe. We can actually arrive to an empty BDD even if there is a solution. But on the whole benchmark, when we tried, this was never the case. And if there is a solution, the optimal solution is present there as well. Good. So now we know how to construct the BDDs with all solutions. We know how to speed it up. So how do we apply it to our failover protection? So the first obvious method is called a deletion. So suddenly somebody gives me the set of failing edges. So what I do, I just take my pre-computed BDD and I intersect it with sort of postulating that none of the demands can use the path that actually contain the failing edge. It's a relatively fast operation, and then I get the prune BDD with all the solutions that avoid the failing edge or failing edges. The slight problem is it's not completely fast. It can, in some cases, exceed this 50 milliseconds, but it's definitely orders of magnitude faster than the ILP. I will show you some plots soon. So we came up with a different solution. So why don't we encode the failing links already into the BDD? So it's actually pre-computed. So in case of one failing link, in my example, I have 7 edges, so I need 3 Boolean variables to encode the failing links. And in the beginning of my BDD, I actually encode what are the options of how they can fail. And if, for example, this is failing, 0, 0, 1, 0, 0, 1, this is H1 is failing, then I have the BDD of all the solutions with assuming that that H is failing. And of course, you can do it for more than one, but then it starts exploding because you need to introduce more and more variables. So we implemented expect all in a Python using the CUDD wrapper. So the wrapper for the CUDD binary for BDD. We evaluated on the Deutsche Telekom and Cantor topologies. We do 1,000 random link failures up to 5 failing links and see how these methods perform. So here are the plots. If I take a look, for example, at the Cantor topology, you can see the ILP fast failover solution. This takes a few seconds. The deletion is initially very fast, but it scales not too good with the increasing number of the demands. The pre-computation, on the other hand, is almost constant. So this is a box plot, so you can see the averages. This is 50 milliseconds line, this is 200 milliseconds line. So we are for sure pretty good satisfying the requirement. In Deutsche Telekom, the picture looks very, very similar. What is interesting on the other hand is the build time. So of course we have to invest in building those BDDs. So what is the build time? So I already showed you if you use the ILP and you would pre-compute everything, this will grow exponentially with the number of failing links as you would expect. This is a logarithmic build time on the y-axis. So in both, this is definitely going to explode. The deletion is very nice because you compute it once, and irrelevant how many failed links you have, it doesn't change. It's a constant. There's a small deviation because of the measurements in the experiment. And the pre-computation is also pretty good. It has a slight, increase with more failing links, but it's not too bad. Of course, what is a little bit bad is that how does it scale with the number of demands? So this is for 7, 8, and 9 demands, and you see we always make a jump that is exponential. So as it is right now, up to 9 demands, we can pre-compute it, let's say, in 1 hour, which is acceptable time because then we are ready within 50 milliseconds to react to any failing links. But of course, the number 9 is a little bit limiting. So in conclusion, we introduced expect all. This is a tool that computes BDD representation of all, including the optimal solutions to the route and spectrum assignment problem. It outperforms the existing ILP approaches both in the query time and build time, but it still suffers from the scalability, and it's not yet applicable for more than 9 demands. So how we can remedy this? Well, we should think more, see whether we can find more restrictions. We still have way too many redundant solutions. So if we manage to find some clever lemmas that say you don't have to do this and that, we can further improve the performance. But what about application in practice? So 9 demands is usually not enough. So what do you do? Well, you can select some very critical demands you want to protect in an optimal way. They should typically be long-lasting and large volume. And what do you do? In the beginning of the spectrum, you simply use this optimal method using BDD. You can pre-compute the solutions. You are guaranteed to have optimal protection there. And for the other demands that are less important, less critical and smaller, we just use some of the existing heuristic approaches, for example, that are not known to be optimal, but we just start to do them from the other side of the spectrum. So that could be one way how to, remedy this, but we would definitely like to work more on improving the performance. Yeah, and that was my 25 minutes, so thank you for your attention.
Thanks for the wonderful talk and being so precisely on time. Yeah.
Oh, I need the mic. So it's really nice. I enjoyed it. So one question I had is, if you already have an ILP, why don't you just take each constraint, make a BDD, and intersect all of them? And you don't need to work so hard to construct a BDD, right? Every constraint is some Boolean values. You could construct a BDD and then just intersect all of them.
I think it's an interesting idea. I think the problem a little bit is, even though these building blocks are small, once we start intersecting them, the BDDs will start growing. And because it's unique, at the end we arrive to the same size of the BDD as we would using the other method.
Right.
So, but yeah.
The other question is, did you have to drop any of the original problem constraints that couldn't fit inside this kind of a BDD? Or, the ILP basically captures everything. The question is does the ILP capture everything, or are there things that are soft constraints, you don't capture them somehow?
The ILP finds one solution. So in the literature, you have all these constraints that it's good, and then you have to set your function you want to minimize, and that can be many different things, but most commonly in the literature, people would like to minimize the maximum slot. So you run the ILP and you get just one solution, and that solution for sure is inside of our BDD. But we offer more. There could be more optimal solutions or suboptimal that the operator might prefer for some other reason. So they can say, I don't want this path to go through Iceland, for example, because the connection is unstable or whatever. So you can put additional restrictions as a conjunction to the BDD and sort of navigate through the space, which I think is the advantage of the BDDs. Yeah.
So, Kedar.
Yeah, thanks. This was really interesting. So I work at Bell Labs, which is part of Nokia. So I don't do this, but I have colleagues who do stuff like this. So I was curious if there are other ways of defining optimality, because one of the constraints I've heard is that you don't want to switch too many paths. That's the optimality criterion. So if a link breaks, then you do have to make some changes, but you don't want to make too many changes because setting up these light paths takes some amount of time. So I don't know if that's correct. This is just something I vaguely remember hearing.
This is excellent question, because I think this is primarily what the operators would like to do. Keep all the paths running and only do the necessary minimum to reshuffle. And indeed, we do it, and we have a section in the paper where we describe how you can optimize it for that criteria and how to construct the BDD. I dropped it because of the lack of time, but indeed, that's something that is possible, and you can read it in the paper.
Then I can use my chairly privileges to ask a few questions. So one thing I was very curious about is how much does the size of your BDD and the computation time depend on things like variable order? Did you have to do any tuning to optimize that? That's one question, and then I have a follow-up.
Yeah. So this is again another excellent question. Of course, the variable ordering is extremely important, and we have tried some smaller models, and we exhaustively tried all the permutations of the variables. Not like there are too many, but there are these blocks like the path, cost variables. Is it better to have path first or cost or interleave them? And actually, this was done by master thesis students, so they spent lots of time, try all the permutation until they found the one that actually works good in this case. And this is first the path, then the cost variables. So if you do it slightly differently, you can get exponentially larger BDDs very, very quickly. Yeah.
And then one thing I noticed is all the integer constraints were kind of bit blasted in a way to make it into the BDD, right? I mean, did you consider using like multi-value BDDs or multi-value decision diagrams to represent the integer?
No, we did not get that far. I think it could be maybe a way how to improve that. I think usually these numbers are not too big. So on a typical network, you have like 320 slots, and then the modulations numbers are depending what kind of modulus, between 2 to 12 maybe. So these are not big numbers to encode. You can do with a small number of bits. So that's why we did not consider that. I don't know if it would speed it up or not. It's something to try. You never know with BDDs or how things behave until you try. So.
Okay, I think that's concludes the time for questions. Please ask more questions offline. And I would like the next speaker to set up this.
Thank you.
Plug this in just in case.
All right, the next talk is going to be given by Devora on constructing trustworthy smart contracts. Looking forward to it. Hopefully the setup is going to be on now.
Okay. Whoa, weird. Okay. Hello, everyone. My name is Devora. I'm a PhD student at NYU. I did this work with Kedar from Nokia Bell Labs, and I'm going to speak to you about a new language for constructing trustworthy smart contracts. So just to give like a lightning overview, a smart contract is a program that can send and receive cryptocurrency on the blockchain. And it's very, very important for these contracts to be written correctly because malicious attackers can exploit bugs in the contract to drain cryptocurrency funds. So we're going to introduce a new language called ASP. It's a non-standard language for contracts that eases verification and makes verification overall much simpler. The way that it does this is by providing abstract types for common blockchain constructs and by giving the smart contracts a state machine structure to mirror blockchain execution. We also have a proof checker so that users can verify contract-specific properties. And then finally, we compile our contracts to Solidity, which is the most popular contract language so that they can be used on standard blockchains. Okay, now if that didn't make any sense to you, don't worry, we're gonna slow down. And let me just give you a little bit of background on the blockchain. Okay, so the blockchain can just be thought of as a decentralized, trustless setting where you can run protocols where you don't want to have to trust a third party to manage it honestly. So if you want to run an election or an auction, let's say, anything that usually needs a third-party trusted manager, you could do that on the blockchain without needing that third-party trust. And the way that you run these protocols on the blockchain is by writing something called a smart contract. Now, a smart contract sounds scary, but it's really just a regular program like we're all familiar with. The only difference is that smart contracts code and state changes are stored on the blockchain. Now, the way that contract execution is triggered is when you have another account on the blockchain that calls a function from the contract's code. Then the function will execute. It could call other functions. And once that whole cascade of execution is complete, then the state changes are stored on the blockchain. If one of the function calls aborts, then the whole thing is reverted. No state changes are recorded. It's an all or nothing deal. Now, a very, very important part of contracts is that they can send and receive cryptocurrency, and that's made them super, super popular. Now, we're in this decentralized, trustless setting. So to preserve the trustlessness, all contract code is completely visible, right? I don't have to trust that your code does what you say it does. I can read it for myself. And code is immutable because I need to know that once I call your code, it's not going to change. But with so much money stored in these contracts, hackers are using the visibility to scour the code for bugs, and contracts are programs, they have bugs. And the immutability ensures that even if the bugs are found, they can't be fixed because the code is immutable. And this has led to just a ton of smart contract exploitation. I think in 2023, it was like $2 billion were lost to smart contract exploitation. Okay, now we need the setting to stay the way that it is. We need the code to be visible and immutable to preserve the trustlessness of the blockchain. So what can be done to prevent smart contract exploitation? You can make sure that your contracts are correct before you put them on the blockchain. So companies like OpenZeppelin, Certora, and Certicay offer static analysis and testing to find as many bugs as possible. But there are no guarantees, and a missed bug can cost you a lot of money. Instead, there are tools like VerX and SmartPulse and 2Viper, and they offer formal verification. But smart contracts are generally written in, the standard languages are complex. Languages are inspired by, C, Rust, they have all these complicated features that we're always dealing with, so the verification is complex. Now, to ease that, things like FSolidM, Scilla, and Move have been developed. These are non-standard languages, and they're designed to simplify the verification. But the problem is that none of these non-standard languages offer robust, accessible verification for standard blockchain contracts. So FSolidM severely limits the scope of verification. You can't verify functional correctness. Scilla proofs are written in Coq, which is generally inaccessible to non-experts. And Move is really, really impressive, but it can't run on standard blockchains. So what is a smart contract programmer to do? So we introduced a new non-standard language called ASP, and this is for writing trustworthy smart contracts. The ASP language does this by providing abstract types for common blockchain constructs like cryptocurrency, tokens, timers, and addresses. Usually these types, if they exist, are represented on a very low level that requires extra verification. But in ASP, these are abstract types, so their correct behavior is guaranteed. And ASP contracts are structured as finite state machines, and that mirrors the state-oriented execution of the blockchain. Now, this all helps simplify contracts in general, But for contract-specific properties, we have a proof checker that can verify safety and reachability proofs. And then finally, ASP contracts are compiled to Solidity so that they can run on standard blockchains. Okay, so that's the overview of the language, and now we're gonna just delve into a few of the particulars over here. So first we're gonna talk about the abstractions. Now, smart contracts are programs, right? So they use a lot of the regular types that we're used to, integers and booleans and maps and all of that. But there are also some blockchain-specific things that they're dealing with. So like I said, one of the most important parts of smart contracts are that they can send and receive cryptocurrency. But in existing languages, cryptocurrency coins don't actually have their own type. They're represented as unsigned integers. Oh, there we go. Now, this is important because once a contract receives cryptocurrency, the code of the contract is going to govern the way that those coins are used. And now that the coins are represented as unsigned integers, a malicious contract can use arithmetic manipulations to obscure the way that those coins are going to be used in the contract. Now, what this means is that if you're writing in a common language like Solidity, your coins are represented as unsigned integers, so your verification is going to require that you're also checking that all of the arithmetic manipulations on these unsigned integers are treating the coins the way that you expect them to be treated. But this is sort of a ridiculous standard because all of these smart contracts are using cryptocurrency. There should just be a type built in for coins. So ASP offers an abstract coin type, which is going to ensure that coins are behaving the way that we expect them to behave. So a coin type in ASP can be thought of as a jar that holds your cryptocurrency, and there are just 3 operators. There's value, so that tells you how much cryptocurrency is in the coin. Move lets you move cryptocurrency from one coin type to another. And move all lets you move all of the coins from one coin to another. And that's it, that's all that they can do. So now instead of having this like verification on the unsigned integers and all the arithmetic manipulation up in the air, you know that this is all that the coins can do. You can very easily follow what they're doing. So this simplifies the verification. I also want to focus on another type in ASP, the timer type. And this is actually sort of an unusual type. I haven't seen other languages offer something similar. So the timer type is going to be helpful for reachability proofs. Now, just a little background, the way that time is treated on the blockchain is time is measured by the growth of the chain. And the blockchain grows sort of in an uneven, non-deterministic manner. So to mirror that, timers in ASP progress non-deterministically. They're implicitly linked to a finite state machine. So this state machine starts in state off. It moves to an active state with the set operator. And then after some non-deterministic number of steps, it's in the state fired. And then you can use the reset to sort of start the whole cycle again. But I'm going to talk a little bit about timers in a while because timers are very, very useful for simplifying reachability proofs. Now, I've talked about the coin type and the timer type. We also have a token type, which is, I find very interesting, sort of unusual, and addresses. And all these abstract types in ASP help simplify verification because the behavior is guaranteed. Now I'm going to also focus on another part of the language that helps simplify verification, and that is the structure of contracts. So contracts are structured as finite state machines, which mirrors the state-oriented, externally triggered blockchain execution. So I'm going to demonstrate with an example of a vending machine. So maybe you start in state pay, you transition to a state order. Now you move to that state by sending the contract cryptocurrency. So the transition from state pay to order takes cryptocurrency as input. Then you can move to a state candy or chocolate, depending on the input message that you send. And finally, you move to a refund state where we send back any extra cryptocurrency that was sent to the contract. And then you can loop back so that a new customer can come use the vending machine. This is like a really nice picture, but when you actually write a contract in ASP, oh, I forgot about this. You can also have transition guards, so guards that limit who can trigger the transition. So you can say something like, the current customer sent the request. Okay, so transitions in ASP can take input. They could have guards. This is like a nice picture. When you actually write a contract in ASP, it looks something like this. So users go state by state. So they'll say what state they're specifying, all the different transition actions that you could take at that state, sorry, like the actual transitions. any inputs that the transition can have. So that last transition doesn't have any input. That's a tau transition. Guards that transition might have. The next state that your transition is taking you to, and then the actions that you take at that transition. Now, just to like explain these, the transitions are all loop-free. So you saw that at the state machine level, you can have a loop. So in ASP, we require users to model these loops explicitly at the state machine level. You can't have loops in the transition actions, and that helps simplify the verification a little bit. Okay, now I'm going to focus on these messages. So we use CCS notation for send and receive. So A, question mark, enter coin C. That's we're receiving an enter coin message from an address that we call A. And it takes in this argument C. So at the beginning of a contract, users specify all the messages and the type. So enter coin has type coin. And then all the way at the end, that last transition sends paid. So we see over here paid, refund is of type coin. So paid is a coin. So we refund the customer the coins that they have sent in. So we're sending back cryptocurrency. And now just to talk for another minute about the coins over here, bring it back to the abstract types. So when we receive this coin, that's someone sending cryptocurrency to the contract. Then we have this move all operator on our abstract coin type. So we move all of the coins that we've received into a coin type called paid. And then we can move the coins around within the contract. So we can move from paid to earnings, either the cost of chocolate amount of coins or candy. And then finally, at the end of the contract, we send the remaining coins from the paid variable back to the customer. And again, the state machine view over here that the contracts take very closely mirrors the state machine orientation of the blockchain. Okay, now I'm going to speak a little bit about the proof checker because the types and the structure overall makes things simpler, but if you really want to make sure that your contract is correct, you want to verify contract-specific properties. So in ASP, we can verify safety and reachability proofs. So I'm going to use an auction contract as an example. So we'll begin in a start auction state. We move to an auction open state. We move to that state by getting a start message by the contract owner. Owner is part of the abstract address type. That's like a keyword. And then we'll set the timer that will govern how long the auction is open. Then we can loop at this auction open state for a while, and we're accepting bids that take a type coin. So people are sending cryptocurrency as bids. And we'll only take that transition when the timer is still active, so the auction is still open, and the value of the coin that they sent is greater than the value of the max that we currently have. And then if that happens, if we take that transition, we'll refund the old max bidder their old max. We'll move all of the new coins into the max coin variable, and we'll set the new max bidder. And then we'll transition to auction close when the timer has fired, and then we send the beneficiary the final max. Now, a property that you might want to verify over here is something like all losing bidders are fully refunded. So this is a safety property. The way that we verify safety properties in ASP is by adding ghost variables. So over here, maybe you'll add a ghost variable bidded that maps addresses to the amount of coins that they've sent in. And a refunded map that maps addresses to the amount that they've been refunded. And the ASP type checker is going to enforce that ghost variables don't influence contract execution. So you can view the ghost variables as the state of an automaton that's going to check for violations of your property. And you can express the property like this. So it's always true that for all addresses that aren't the max bidder or the beneficiary, the amount that they've been refunded is equal to the amount that they've bid. So that's expressing our safety property. And now the way that the proof checker is going to check this is by compiling the contract and all of the ghost state and the assertions into the Viper verification tool. So the way that we do that is we go transition by transition. Every transition in ASP becomes a method in Viper. And the proof checker compiles these Horde triples of precondition, transition action, postcondition, and the Viper verification tool will check that, given the precondition, if you take the transition action, that will guarantee the postcondition. If you need state-specific assertions to support your global invariants, ASP also supports these state invariants that will also get compiled to Viper and checked along with the global assertions. So those are the safety properties. Now you also might want to prove a reachability property, like we'll always reach auction closed. And the way that we prove reachability properties in ASP is by using the timer type. So the way that we do it is that users will write the set of states for reachability, so we'll call that R, a state assertion theta, I'll get into that in a second, and a well-founded ranking function rho. And the proof checker is going to check that theta holds for the initial state, that the ranking function rho is defined for every state in theta in the assertion that's not in the reachability set. And for every such state that's in the state assertion not in the reachability set, there exists an enabled transition at that state. And for every transition from that state to a next state, either the next state lands us in our reachability set, or the state assertion holds at that next state and the rank strictly decreases. So altogether, what this means is that the state assertion is sort of going to color in all of these states on the way to the reachability set, and now requiring that the rank strictly decreases along with the fact that the rank is well-founded, so you can't have an infinite decrease. That gives us this proof system that we're guaranteed to reach a state in our reachability set. So just back to the auction contract, like a first thought ranking function just is like counting down the number of states until auction closed. But we need the rank to strictly decrease, and that loop over there at auction open won't be a strict decrease. It'll just take us back to 1. So we add a dimension. So start auction will have rank 2, 0. Auction close will be 0, 0. And then at auction open will differentiate. It'll be 1, 0 if the timer has fired and we reach that reachability set, and 1, time left if the timer is still active. Now, how do you know that time left is decreasing? So that's guaranteed by the abstract timer type. The abstract timer type, the semantics are going to guarantee that the time is always decreasing. And now to model time accurately on the blockchain, time should be decreasing even if no one is sending in bits. So the ASP proof checker adds in an explicit time transition. So any state that has a timer active will also attach a time transition that will decrease the amount of time that's left on the timer. Now you might look at this and say, this is very nice, but what about this first transition from start auction to auction open, right? We need to take a transition. We need that input of a start message by the owner. And if the owner just never sends us that start message, then you won't reach auction closed. Okay, that would be a very good complaint. So actually looking at the proof system that we have, all that our reachability proofs show is that for every maximal computation that we take from the contract, you'll definitely reach a state in your reachability set. But the reachability proofs are not proving that you must take those maximal computations or even that you always can. Now, in the auction contract, that's like not a big deal. If nobody starts the auction, like the world won't implode. But in our vending machine example, at state order, we require that the current customer sends a request. And if a current customer just walks away and never sends a request, then everybody else will eternally be locked out of this contract. And that would be very sad. Now, this is an adversarial lockout property. And it's also a little advertisement for the paper. So in the paper, we have a proof system for proving the absence of adversarial lockouts. Go see it. It's very interesting. We're in the process of implementing that as a proof system that an ASP user can use. Happy to talk about that some more afterwards. All right, finally, once you verified a contract in ASP, we compile it to Solidity so that it can be run on a standard blockchain. And what we want to know is that once you verify these properties in ASP, those properties should still hold once it's been compiled to Solidity. And our compiler is going to guarantee this by preserving the semantics of the ASP contract in compilation. So the first thing it has to do is we have to go from the state machine view of ASP to the function-based view of Solidity. So every message in ASP becomes a function, a public function in Solidity. And again, the messages are things people send to the contract. Functions are things that people call from a contract, so that's like the one-to-one. Then we do a case analysis on the state to determine what action to take given the message and the state that we're in. So, if you try to call a function, that isn't in the appropriate state, it will revert. And then if you're in the proper state, then it will give you the transition actions that you take. And then the other thing that we have to do is we have to add runtime checks to ensure that the Solidity contract is respecting the abstract types and the behaviors of the ASP contract. Now, if a runtime check fails, that will also revert the transaction. So with these reverts, we end up with a language inclusion property. So not language equivalence, but inclusion. So every successful transaction of a compiled solidity contract, meaning it doesn't revert, has a corresponding execution contract in ASP. So what this gives us is that safety properties in ASP are going to be true. Once they've been proven in ASP, they also hold for solidity. And for the reachability properties, assuming we're taking those maximal computation and you're not reverting transactions, the reachability properties proven for ASP will also hold for the compiled solidity contract. So users can rely on the verification at the ASP level for the solidity code. Now, just to sum up, ASP is a non-standard contract language that leverages abstract types and a state machine structure to simplify verification. The proof checker lets you verify contract-specific safety and reachability properties, and then it's finally compiled to solidity so that it can run on a standard Ethereum blockchain. ASP is going to be open source. We just got like the industry approvals that we need, but there's like holiday backlog, so it won't be up for like another week or two. In the meantime, we have example contracts here or open source in a few days. I guess that's probably optimistic. It's probably more like a week or two. But you can check out the example contracts in the meantime. We'll have a tutorial up once the language is open sourced also. The example contracts here are modeled on contracts in other languages so that you can sort of see the difference between ASP and these other languages. I want to thank these artists from Noun Project. That's a great website. That's where I got all of my graphics. A lot of credit to these people. ASP is still evolving as a language, and we would love for people to give us feedback, try it out, play around. Yeah, and happy to take any questions. Thanks.
Thank you for the very interesting talk. If I can, maybe two quick questions. So the state machines, they are over some abstract data types. They look like finite. So is this true that the whole system is finite state?
Yeah. It's a finite state machine, yeah.
Okay. Yeah, so that's, and then it looks like very good that you solved the problem of somebody inserting the malicious code, because now everything is verified. How do I know that your compilation did not introduce a malicious code? How can you convince the blockchain users that your translation is actually, as you claim, safe for them?
Yeah, no, it's a good question. I mean, the language will be open source, so that will include the compilation to Solidity. It's a pretty straightforward compilation. We're not putting the open source on the blockchain because then we can't modify it. But it's open sourced and available for everybody to see how we compile it to Solidity. So, yeah, but if you don't want to read through
the case for the others. You could also see the code before you put it on the blockchain, and people did not see the problems, and now.
Well, there's just so the difference is that in contracts that people are exploiting, so you can read the code, but you want to verify that the code is bug-free. Over here, we're saying, you can see the way that we compile ASP contracts to Solidity, and then the Solidity code will go up on the blockchain. So you do have that compilation step, but the compilation is pretty straightforward, and the open source will let everybody see the way that the contracts are compiled. You can look at the compilation for yourself. So, yeah. Does that make sense?
So maybe a quick follow-up question
Yeah.
Is the compiler from ASP to Solidity something that you protect, or can people write their own compiler, which could potentially, produce bad code?
Oh, I see what you're saying. As in, you want to know if somebody else writes a contract in ASP and says, oh, this is the compiled Solidity version, but it's not the compiled Solidity version. I understand. So what anyone could do is and then you want to know, they're not posting the ASP code to the blockchain, only the Solidity code. Yeah, that's a good question. If people make the original ASP code available, then anyone could run it through our compiler to get the compiled Solidity code and verify that the compilation is correct. But if they don't put up the code, then I guess that would be a reason to be suspicious that it's not the original, the true compilation. Yeah.
Yes. So in smart contracts, many of the bugs or attacks are not so much about a problem in a method, in a pre-post condition, but the interaction with other contracts or the power of different agents. So in one of your examples, you were expressing the property every participant will be refunded. so which seems like a temporal property. But I will try to do a follow-up question. How did you implement that?
Oh, the
So you could prove it.
all losing bidders, that one? We'll go all the way back to that. Here, okay. Oh, here we go.
Yeah.
Okay, so over here we verify this property with this ghost variable, with the two ghost variables that are mapping every address to how much money they've sent in and how much they've gotten refunded. So this property is expressing that the amount that everybody has sent will equal the amount that they eventually get back, assuming they're not the max bidder or the beneficiary. But the question they were asking about interacting with other contracts is a very good question. So right now, really ASP contracts, you can verify behavior of a bunch of interacting ASP contracts in terms of behavior of, once you have the compiled Solidity contract, and then maybe that's going to interact with other contracts. So that's not something that we've done so much on yet, but is like a very good future work for us to do.
Rephrase the question or try to follow up on the question. So for auction contract, to prove the property, two things have been attempted to try to have such a property. One is to go through a loop where you have all participants and then you try to refund the money, and then there are attacks. There are well-known attacks like gas attacks. For example, you go and participate as a bidder, bidding a cent until the list is so long that when someone tries to run the refund, no one gets money because you run out of gas. So I'm attacking the contract by adding 1 cent with different addresses, making a list too long.
Okay.
So if you're not gas precise, then my attack will be effective and no one gets the money. I participated with cents, fools participated with millions, and the money gets locked in the contract. So what people do in modern implementation of auctions is to have a vault. So at the end of the day, you have an array, and then participants can go and fetch their money if they will, if they wish to. But then the property is not like this. The property is like every participant has the power to get the money in spite of what the other participants do, which is not the temporal property. It's more like an ATL kind of property where you have to talk about the power of participants as coalitions or individuals in spite of what the other participants do. And then your proof system is completely different because you need to talk about the different agents, right?
So
maybe a long question.
Yeah, so in this contract, we're actually not taking anyone's bid unless it's dethroning the old max. As in, there are a lot of auction contracts where you collect all of the bids and then at the end of the day, you send all of them back. So this contract isn't doing that. We don't take any money unless it's a new max, and then we immediately send back the previous max.
But then there is an attack. That has been attempted too. I refuse the money and fail. So if you try to refund me the money because I have been overturned by another bidder, then I refuse to collect the money and fail a transaction. So I'm still the highest bidder. Because I can fail a transaction because when you send me the money, then I have the power to fail. I have the power to reject it and fail.
Oh, you're talking about the different ways of sending cryptocurrency back once we've compiled to Solidity? Yes. As in there are different, right? Okay, yeah, so on the compilation to Solidity, which precise one we use, Kedar, I can't remember which one we're using. Yeah.
This sounds like a very interesting discussion to take offline in the interest of time. So let's please thank the speaker. It was a wonderful talk.
Hello everyone, my name is Yuncheng Wang. I'm a PhD student from the Institute of Information Engineering, Chinese Academy of Science. Our work is automated flow detection for industrial robot REST service. Industrial robots are mainly composed of three parts. The first is a manipulator, such as the orange machine on the left of the right image. Then there is a controller, which is an embedded device. Finally, the programming interaction part is used for field control or offline programming. Industrial robots are applied across a wide range of critical industries. They are often used in collaboration to create automated production lines, such as those found in automotive manufacturing, electronic assembly, pharmaceutical production, and logistic sorting. According to the 2023 World Robotics Report, the number of industrial robots in worldwide has exceeded 3.9 million units. Since industrial robots are a critical component of production lines, the downtime of a single robot can halt the entire production line, leading to increased operational costs. These unexpected downtimes can result in losses of up to $10,000 per minute. When industrial robots were first designed, they operated within a closed local network. Programmers would write the robot programs and the operators would debug them on site. However, with the increasing openness of industrial environments, industrial robots are now being integrated into enterprise networks and even the internet. Network users are expected to interact with robots through open interfaces. While this trend has improved real-time communication between users and the robots, it has also disrupted the securely closed environment. Industrial robots often lack robust security mechanism to defend against cyber attacks in the open environment. Adversaries can exploit this network interface as entry points to access the robot controller. Once inside, they can leverage potential vulnerabilities in the controller to launch attacks, causing significant damage. Currently, the most popular network interface in the REST API is lightweight, flexible, and convenient design for managing and accessing web resources has made it the preferred choice for industrial robot network interfaces. REST stands for Representational State Transfer. In REST architecture, data and functions are treated as resources, which can be accessed using uniform resource identifiers. Client and server exchange resources through standardized interfaces and protocols. HTTP is the most commonly used protocol. Third-party services or networks users act as clients and send CRUD requests. CRUD is create, read, update, and delete the server. The server processes these requests, performs the necessary actions, and then responds, typically with a JSON payload. A REST request is constructed with the following components: the operation endpoint, parameters, and handlers. For example, in the bottom graph, the operation is get, the endpoint is RW repeat symbol, and so on, with two parameters named symbol URL and value. REST provides a set of guidelines and controls for developing applications. It also comes with a standardized documentation known as the OpenAPI specification or Swagger specification that tells the users how to interact with REST APIs. The OpenAPI specification is typically stored in YAML or JSON fields, which contain information about the API endpoint, available CRUD operations, input parameters, response descriptions, and more. In industrial robot, REST API server has a powerful interface. External requests can directly access the robot controller through REST API, enabling control and programming of the robots. This includes tasks like accessing and modifying files, reading and setting I/O signals, reading and modifying robot programs, and much more. Despite these powerful capabilities, security mechanisms are often lacking, and when security issue occurred, the consequences can be severe. Since external requests directly interact with the robot controller, they have a real impact on the physical space and directly affect the robots in the field. Given these powerful functionalities, we have some security concerns. Are there any flaws in the implementation of the REST service? For example, could there be mistakes or potential vulnerabilities introduced during implementation? Second, has the system been thoroughly tested for security to ensure its reliability? And are there proper checks in place to validate the range of the request parameters? So to address these concerns, we conduct tests on the REST service of industrial robots to identify potential security issues. We focus on detecting bugs that could trigger internal server errors and vulnerabilities that could lead to a denial of service, causing the robot to shut down. However, performing efficiency detection comes with three major challenges. First, how do we generate high-quality test cases? The main goal of testing is to explore the different states of the server at various depths. Therefore, a key challenge is ensuring that the input parameters in the test sequence are correct so that the server can process external requests effectively, allowing us to test its deeper states. Second, how do we achieve high throughput testing? The testing space for REST API is vast, and sending a large number of requests to the server in a short time can consume significant resources on the controller. Since the robot controller is an embedded device with limited resources, they have strict session management and request limits. So executing a high volume of REST requests in a short time is really a challenge. Finally, how do we detect abnormal states in the robot? Robots are typically several physical systems. Its physical abnormal states is difficult to be observed by the program. So we aim to provide a high-throughput black box testing tool for industrial robot REST service to uncover flaws in robot controller. We have three key motivations to help us achieve this. Firstly, each operation and parameter in the OpenAPI specification may include a description field, which often contains valid examples of parameter values. This can be used to generate high-quality test cases. For example, the text circled by the green box in the graph can be used as the value of parameters. Next, we found the session resources are susceptible to hijacking. We can implement an active man-in-the-middle forwarding mechanism to bypass resource limits. Finally, since the robot controller is a physical entity with clear on-off previous states, we can use this as a physical space anomaly indicators. Based on these motivations, we build a prototype system called RobRest, which consists of 2 stages and 4 modules. In the pre-processing stage, we use a parsing module to analyze the OpenAPI specification documents, extracting dependency relationship and parameter information. In the fast testing stage, we force the user generation module to create test cases based on the information extracted in the pre-processing stage. These cases include both single requests and sequences of multiple requests. Next, a forward module is built between the testing plan and the server, enable us to bypass resource constraints on the controller and perform high-throughput testing. Finally, we observe the state of the industrial robot controller using both cyber and physical indicators to detect anomalies. When the controller triggers a denial of service condition, we conduct post-processing to reset the controller and spot automated testing. The first step in our approach is to pass the OpenAPI specification to extract two key information, a dictionary of parameter values, and three types of dependency relationships. For building the parameter dictionary, we extract useful information from the description fields of each operation and parameter in the specification. These fields may include valid parameter values, and the operation description fields provide the information applicable to all parameters within the operation, and the parameter description field offers the detail specific to the current parameter. For example, as shown in the image, the blue section of the post operation contains some simple values, such as TPFK1, TPFK2. We extract all parameter value name from the endpoint and perform knowledge extraction on the description field to identify possible values for each parameter. Similarly, for each parameter's description field, such as the green section, we directly extract possible values from the description and use them to build a candidate dictionary for current parameter. And we use a large language model as knowledge extraction tools for this task. We also identified three types of dependency relationships. First, CRUD relationships. This describes the order of operation for the same schema. For example, a create operation should precede read, update, or delete operations, and a delete operation should come last. Second, schema relationships. If an attribute P1 is one schema S1 is equivalent to an attribute P2 in another schema S2, it indicates that the two schemas are related. Thirdly, if a resource in the response of API A is used as an input parameter for API B, then we say that B depends on A. In this case, A is called the producer and B is the consumer. We refer to this producer-consumer relationship as a data flow dependency. Next is the generation module, which handles two key tasks: sequence generation and request construction. Based on the three types of dependencies, we generate appropriate request sequences. For instance, as shown in the graph, both API use the same schema, OP mode. In this case, the GET request acts as the producer and must be executed before the POST request, which is the consumer. So we can obtain a request sequence, get RW panel OP mode, and post RW panel OP mode acknowledge. After generating the request sequence, we need to provide input parameters for each request to ensure it can be processed by the server. RobRest assigns the values to input parameters based on these rulers. First, if the request has been successfully executed before, we reuse the parameter values from the last successful run. Second, if the parameter exists in the dictionary we built earlier, RobRest randomly select a value from the dictionary corresponding to the parameter name. Thirdly, if the parameter for one operation depends on the response of a previous operation, we wait for the early operation to complete and retrieve the required value from its response. Otherwise, if none of the above applies, we assign the random value as the parameter value. For typically REST service deployed on cloud platforms, the previous steps are sufficient for fast testing. However, robot controller imposes strict resource usage limits. They reject excessive requests in a shorter period, and if overloaded, they refuse to accept any new requests. This drastically reduces test efficiency. We discovered that the server performs two types of checks on incoming requests. First, legitimacy check. This ensures requests include valid authentication, second resource quarter check. This verifies that the session ID is in the request doesn't exceed the maximum limit. To bypass these constraints, we use a forward module. This module modifies the request date and reuses the session ID from the first successful request to construct subsequent request handles, effectively bypassing the resource quarter check. Specifically, we use a sniffing message with correct functional fields and authentication information to establish a connection with the robot service. Once connected, we record the server's response and reuse session information for all subsequent requests. The last module is robot monitor. We use two types of metrics, cyber and physical, to detect abnormal states in the robot controller. For the cyberspace, just like other REST testing tools, we rely on the HTTP status code to identify server-side internal errors. For the physical space, when the robot controller becomes unavailable, the robot typically enters a closed state. This closed state serves as an indicator of an exception. But this physical state change happens in the real world, where it is something a human observer can spot with their own eyes. A programmer can't directly detect it, so we need to translate it into a program readable signal. To achieve this, we use other program events that happen at the same time. Here is a key insight. The controller is actually a Windows-based system, and during this process, Windows socket errors are generated. Using specific socket error codes, like a connection aborted or connection reset, we can automatically detect when an error occurs. Finally, during test, if we find vulnerabilities that lead to a denial of service state, we need to restore it to a normal state to continue testing. To do this, we documented every step required to restart the controller, including the UI buttons that need to be clicked. Then we use AutoIt to simulate mouse clicks and reset the robot. To evaluate RobRest, we pose the three key research questions. First, how much does RobRest improve flow detection efficiency compared to existing work? Second, how much does RobRest improve API operation coverage compared to existing works? Third, how effective is our parameter candidate dictionary in detecting flaws? We conducted experiments on ABB's robot web service. Each experiment lasts for 12 hours and was repeated 5 times. For research question 1, RobRest identified 19 flaws in total, with 2 vulnerabilities receiving CVE ID. Compared to existing tools like RobRest and Zip, our approach detected 9 and 13 additional flaws. In addition, 4 vulnerabilities were discovered through physical states. For research question 1, RobRest achieved a 30.94% improvement in API operation coverage compared to the data with the ART tool. It also detected 90% more flaws. To validate our dictionary strategy, we conducted ablation experiments with 3 RobRest variants. They are removing all dictionaries and removing only one dictionary. The result of clear combining both operation and parameter descriptions led to the highest success rate for API requests and uncovered the most flaws, where parameter descriptions provided more usable values than operation descriptions. Both were essential for maximum coverage and flaw detection. Okay, to wrap up, let me summarize our work. We conducted the first systematic study of system flaws affecting the availability of industrial robot REST service. We developed an automated testing tool called RobRest, capable of detecting bugs and vulnerabilities in robot controller REST service. When applied to ABB's RWS, RobRest uncovered 4 vulnerabilities and 15 bugs, and we responsible disclosed all these flaws to the developers and obtained their confirmation. Our work can have a serious impact on the real world. The vulnerabilities when discovered exist into mainstream industrial robot controllers. Exploiting these vulnerabilities could affect nearly all ABB industry robots, leading to denial of service attacks and significantly disruption in production processes. Okay, thank you for your attention, and I'm happy to take any questions.
Hello? Yeah. Okay. Are there
Hello?
questions? Okay. Hi. So maybe let me ask a question. So among the kind of bugs that you discovered, was there some kind of a pattern to these bugs that you found? Like, I mean, was it more correlated? Was it more useful to use the parameter dictionaries or the other kind of dictionaries to uncover these bugs?
Oh, sorry, can you repeat it? I don't understand.
I was wondering if there was some pattern to the kind of bugs that you discovered and the vulnerabilities. Did you find one of the two approaches that you presented, and then in the ablation study? Do you have a sense of which of those approaches is more effective at finding the bugs?
Oh, sorry, my spoken English is not good, and I don't understand the last words.
Maybe let me simplify the question. I'm just curious to know if there was some pattern to the kind of bugs that you found.
Oh, you mean the evaluate object?
Yeah, I mean, in the last slide, you had like a list of vulnerabilities and bugs. So was there some kind of common pattern among them, or they were all kind of different?
Those my last slide.
Yeah, in your experimental results, you showed that there were some vulnerabilities and some bugs. I mean, is there some kind of a pattern that you found that was common among those?
I think maybe they are not.
Okay. Any other questions? Okay, then in that case, we thank you for the talk and thank you for attending remotely. And that concludes the session for today.
Oh, okay, so thank you.